this is actually a piece of advice I got from Natty Seiberg, was that you should learn the physics from the physicists. And I think the converse of that is also true. You should learn the math from the mathematicians. And I think that there's a lot of benefit in, quantum mechanics class, quantum field theory class,
Mhm.
working through the problems, working through the exercises. And conversely, I think it's very beneficial to learn, say, algebraic topology from the mathematicians. You
Mhm.
know, there's a lot, physicists use things like homology and homotopy groups and things like this very cavalierly. Um,
Yes.
and I think if you really want to feel confident with those subjects, you should learn them from the mathematical perspective.
The guest of today's podcast is Dr. Jacob McNamara. He is a theoretical physicist at Simon Center for Geometry and Physics who has worked on Swampland, Cobordism conjecture, holography, and non-invertible symmetries. So let's welcome Dr. McNamara on the podcast and listen to what he has to say. So, Dr. McNamara, welcome to the podcast. Nice to have you.
Hi, thank you very much for the invitation. It's great to be here.
So, this is the question that I ask anyone when I start the podcast. So, before we talk about anything else, can you tell us a bit about the projects that you're working on nowadays?
Yeah, so there's one project I'm working on right now. We're finishing up the paper. It's something I've been talking about at conferences for maybe over a year now, so probably time to get the paper out. Um, we're trying to understand the breakdown of factorization of Hilbert spaces in holography. So there's this factorization paradox in holography where if you have set up a quantum gravity system with two different asymptotic regions, you can have wormholes that connect the two asymptotic regions, and those wormholes look like they break the idea of holography, which would be that the system is really just a disjoint system on one boundary and another system on the other boundary. So we've understood for a while how factorization for the partition function works. This is going back to work of Coleman. And so the project we're working on basically answers the question of how does the factorization of the Hilbert space break down? This is related to ideas like ER equals EPR.
Right. So, correct me if I'm wrong. The
Mhm.
paradox is that the partition function on the bulk side is not factorizable, but the partition function on the boundary side is factorizable, right?
Yeah, I might phrase it slightly differently. I would say
Mhm.
that the partition function, as you might try to calculate it by thinking of it as a sum over space-time manifolds, looks like it doesn't factorize. Um, if you had something like string theory in the bulk, we believe that it would factorize into the product of the two things on the two sides. So the paradox is how does something like string theory avoid the breakdown of factorization coming from wormholes?
Right. So,
Yeah.
so you're talking about the scenario where you have, a bulk space-time with two boundaries, right?
Yes.
And you have a boundary theory on each
Hmm.
boundary, and the factorization on the boundaries, of course, that factorizes, but the bulk.
Hmm.
Okay, I see. So, um, okay. So since you haven't, put out the paper yet, but what are, what are the insights that you have about the factorization of Hilbert space?
Yeah, so it's actually connected to other things I've worked on. So basically, the conclusion is that if the Hilbert space doesn't factorize, then the reason it doesn't factorize is that you have an incomplete spectrum of states, of charged states. So technically, the result is that you can pull out using some techniques from category theory, you can construct a group, and you can find that the theory does not factorize because there are wormholes, Einstein-Rosen bridges, which don't have charged one-sided microstates. And so the only way the factorization can break down is if you have an incomplete spectrum of states. And so this connects the idea in the Swampland program that a UV complete theory of quantum gravity should have a complete spectrum of charged states.
Right. Uh, we will get more into this, but does it have anything to do with, the work on R7 branes that you and some other people have done?
Uh, in spirit, yes, not so directly. But in spirit, the motivation for uh, our Cobordism conjecture, for absence of global symmetries, for completeness of the spectrum, all of these sort of kinematic swampland conjectures are really all one principle. And they really follow very directly from holography. So we can get more into that if you want.
Sure. So I think we should get into Swampland. So
Mhm.
I'm pretty sure that most of the audience of this podcast does have an idea of what Swampland is. So, but still, can you tell us a bit about what the Swampland program is, and specifically, let's talk more about the no global symmetries conjecture because that's going to be central. in our discussion.
Totally. So the Swampland program, the basic premise of the Swampland program is to understand the space of all quantum gravity theories. Um, the sort of basic guess or conjecture underlying the Swampland program is that there are many things that look like consistent quantum gravity theories at low energy, so many consistent low energy effective field theories coupled to gravity. But most of them are not actually consistent. And so the set of actually consistent UV complete quantum theories of gravity would be much smaller. And so that smaller set of actually consistent theories we might call the landscape. Maybe we'd call it the string landscape. And the complement, the theories which look good but are actually inconsistent, we would call the swampland. And I think there's two main reasons why you would want to ask this question. Um, I think for a lot of people, the main motivating drive for asking this question is connection to phenomenology. So it's an old complaint about string theory that string theory is compatible with anything, and if anything goes, then it's not predictive, then it's not science. And I think this is fair. If that were true, if string theory was compatible with anything, I don't really think it would be science. Um, but because of this belief, because we think it's not consistent with everything, then you can try to find principles, find ways to distinguish the swampland from the landscape, and then use those to make predictions, use those to actually learn something about phenomenology. Um, my main motivation actually is not from the perspective of phenomenology. I'm interested in phenomenology, but it's not the sort of main driving reason why I think about the swampland. For me, the swampland is a way at getting at what is UV complete quantum gravity? What is the structure of UV complete quantum gravity? And so these consistency principles, which we could use to distinguish the swampland from the landscape, are also things that we can try to use to understand just what is quantum gravity formally in the first place. And so that's what I'm interested in. Yeah. Um,
Yeah. So you were going to say something?
well, I realized I didn't answer the second part of your question about no global
Mhm.
symmetries.
Sure.
Um, so no global symmetries is, I think, in many ways, the most important or one of the most important swampland conjectures. Um, I think it's actually really kind of an old idea. It actually, I think, goes back to an idea of Leibniz that which is called the indistinguishability of indiscernibles. The idea that if you can't tell two physical situations apart by any means, then you should identify them. Then they should be the same.
Yeah.
And so this is something that I think we learned also from Einstein, the idea that everything is relative, everything needs to be, there's no sort of sense of absolute physics. Everything in gravity, everything needs to be defined in a relative way. So no global symmetries is a formalization of that. It's the statement that if you have any symmetry in quantum gravity, it's not a global symmetry, meaning a transformation that takes you from one state of the system to another. It's actually a redundancy. So if you have two quantum gravity scenarios that are related by a symmetry, actually those are identified. So it's what we call a gauge symmetry. So this is the idea of no global symmetries. There's more direct ways, more sort of down to earth ways to get to it. But I
Sure.
think it does go back to this sort of philosophical reasoning.
So let's also talk about the completeness of spectrum
Mhm.
conjecture. What is that?
Yes, so the completeness of spectrum. So these, maybe I should also say, these conjectures we're talking about are what I might call kinematic swampland conjectures. I think a useful division of the swampland is into uh, kinematic conjectures, which are about the qualitative features of the theory, things like what particles exist, what states exist, what symmetries exist. And then there's also the dynamical side of the swampland, which are statements about energetics. So if a particle exists, what energy it is. These are things like the weak gravity conjecture. Um, and so most of what I focus on is the kinematic side. So the next kinematic swampland conjecture you just mentioned,
Hmm.
completeness of the spectrum. So this is the idea that in quantum gravity, sort of the flip side of no global symmetries is that anything that can go should go.
Hmm.
And so completeness of the spectrum says that if there is a consistent charge that can be coupled to the theory, say if your theory has, let me give a real world example. So the real world has electromagnetism. And electromagnetism theoretically allows for a monopole, so a magnetic monopole. We've never found a monopole in our universe, but the conjecture is that a consistent theory of quantum gravity must include dynamical charges of all possible charge, including, for instance, in our universe, a monopole. One argument for that is that in our universe, we can write down, at least in the standard model, coupled to gravity, we can write down a magnetically charged black hole. And once you have a magnetically charged black hole, that black hole better be made of something. And the only
Hmm.
thing it can be made of, if it has some net magnetic charge, is monopoles. It has to, somewhere inside, it needs to be built from monopoles. And so that's the basic reasoning of completeness of the spectrum.
I see. So, one question that I have is
Mhm.
that all these swampland conjectures, so specifically the two swampland conjectures that we talked about, the no global symmetries conjecture and the completeness of spectrum conjecture, are they independent?
No, certainly not. And this is something that I've thought a lot about.
Hmm.
So the two we just mentioned, no global symmetries and completeness, are very directly related. And so we've learned that there's something called a higher form symmetry or a generalized global symmetry. This is a symmetry. So normal symmetries, what we call zero form symmetries, are symmetries where the charged excitations of the theory that carry that charge are particles. So something like electric charge or baryon number or something. This is a zero form symmetry because the particles are zero-dimensional objects in space. A one-form symmetry is a symmetry where the charge objects are extended in one dimension. So strings could be charged under a one-form symmetry, or field lines, say of an electromagnetic field, are charged under one-form symmetry. And breaking the one-form symmetry is saying that those field lines can end. And so if we say that there's a one-form symmetry, take the same example under which magnetic field lines are charged, then breaking that symmetry means that you need something on which magnetic field lines can end, which is a monopole. So there's a really direct one-to-one correspondence between absence of one-form symmetries and completeness of the spectrum of particles. You could keep going, absence of two-form symmetries and completeness of the spectrum of strings, so on. Um, More technically, to make this connection really one-to-one correspondence, we showed in a paper that what you need to do is you need to also include what's known as non-invertible global symmetries. These are symmetries which are more general than a group law. They correspond to transformations of the system where you don't just sort of rearrange the degrees of freedom, but instead you take some of the degrees of freedom and throw them out and pull out some new degrees of freedom. And then when they recombine, you get the same physics. So that's a non-invertible symmetry.
Hmm.
We've learned that some sorts of charges correspond to non-invertible symmetries rather than invertible symmetries. And so if you want completeness of the spectrum of all kinds of charges, you need both invertible and non-invertible symmetries.
So, correct me if I'm wrong, but
Mhm.
you have to include non-invertible symmetries when you have any gauge group which is not abelian, correct?
Not just it's slightly more than just non-abelian.
Okay.
You need it to be sort of non-abelian and disconnected. Um,
Okay.
there's a more technical statement I could make, but for a
Hmm.
connected abelian group, you always have gluons. So say in the standard model, we have the strong nuclear interaction, the gauge group is SU3, and you have, this is a connected group, and you have gluons, and gluons generate all of the charges that are not protected by a invertible one-form symmetry.
Right.
So for a connected group, you only have to look at invertible symmetries. But once you start thinking about disconnected gauge groups, that's when you start needing to think about non-invertible symmetries. So an example would be O2 gauge theory. This is what's known as Alice electrodynamics. Essentially, it's just electromagnetism, but with charge conjugation also gauge. So the symmetry that takes, E to minus E, B to minus B. That symmetry, if you gauge that, you get what's called Alice electrodynamics. In order to derive completeness of the spectrum of charges in Alice electrodynamics, you need to think about non-invertible global symmetries.
So even if you have, several components of the gauge group which are disconnected, but each of them is abelian, even then you would need
Even then,
non-invertible.
then you would be fine with just invertible symmetries.
Okay, I see.
Basically, the way that non-invertible symmetries come into the game um, is if you have, I think how to say it. If you have conjugacy classes in your group, which have a non-zero but finite number of elements.
Hmm.
So whenever you have such a conjugacy class, you get a non-invertible symmetry. Um, and in order to have a non-zero, not just one, but multiple elements in a conjugacy class, your group has to be non-abelian.
Okay, I see. So wait, so are you saying that there should be a finite number of elements in the conjugacy class, or the number of conjugacy classes itself should be finite?
The precise statement is that the conjugacy classes which correspond to non-invertible symmetries are the ones of finite size. Sorry,
Oh,
the,
okay.
of symmetries are the ones with finite size. The ones of
Mm-hmm.
infinite sizes aren't even symmetries because gluons break them.
Yes.
The
Okay.
ones of finite size are symmetries. The ones whose size is one are invertible symmetries.
I see. I see.
Another way of saying is that the conjugacy classes consisting of one element correspond to the center of the group. Conjugacy classes with a finite number of elements correspond to what's known as the centralizer of the identity component.
Mm-hmm. I see. So, um, what about non-compact gauge groups?
So for non-compact gauge groups, the statements get a little bit more difficult to make. But we also believe in quantum gravity that the gauge group had better be compact anyway.
Mm-hmm.
Um, the physics reason for this is that we believe that the entropy in a finite region of quantum gravity is a finite number. Because if you tried to put more information, put more entropy in a region than the entropy of a black hole of that size, then you would create a bigger black hole, and so you wouldn't have succeeded in putting it in the region you started with. Um, the point being that when you have a non-compact gauge group, the sort of amount of entropy in any finite region is infinite. And so if you
Mm-hmm.
want the amount of entropy in a finite region to stay finite, you had better expect the gauge group to be compact. Um,
I see. I see. Okay, so let's talk about Cobordism conjecture.
mhm,
I
mhm.
mean, it does relate to one of the works that you did with your advisor,
Yes.
Komor, I think
Yes.
in 2019, if I'm not wrong, right?
2019, yeah, fall
Okay.
2019.
So what is Cobordism conjecture?
Yeah, so the Cobordism conjecture, first of all, I should say I think there are a number of different perspectives on the Cobordism conjecture. I'm happy to talk about them. The
Hmm.
one that's most closely related to what we just were discussing is that the Cobordism conjecture is an attempt to formalize what we mean by all possible charges. So we said before that in quantum gravity, we expect anything that can go should go, any charge you can have, you should have. Um, and if you want that to be a precise statement, you need to know what it means, what any possible charge means. And so the way that we formalize this notion of any possible charge is that we say, well, what's a charge? A charge is something, or a gauge charge is something that if you had a black hole, you could measure by looking just at the outside, at the horizon of the black hole. This is sort of a generalization of Gauss's law. Gauss's law tells us that if we have, say, again, a magnetically charged black hole, then we know there's a monopole inside because we can measure the magnetic field through the horizon and tell that there's a monopole inside. So the Cobordism conjecture takes that idea and generalizes it. It says that we're going to instead define charge to be a property sort of the horizon manifold. So if you have a black hole, you can look at its horizon. So that's some closed, for a black hole, it would be a d minus 2 manifold in d dimensions, so a surface in 4 dimensions like we live in. Um, so that's some manifold. And we want our charges to be conserved. So conserved means that it's a preserved property of that manifold up to any possible deformations of the manifold. And in particular, one possible deformation you could have is it could split and join, or its topology could change. So if it splits and joins, you would say that, well, you're just saying you have some total charge, you split it into two pieces, so the total charge is conserved. But more generally, if its topology changes, which is something that can happen in quantum gravity is the theory of quantum mechanical spacetimes, um, then as its topology changes, you want its charge to remain the same. So cobordism is a mathematical notion that says that takes it's an equivalence relation on manifolds. It says that two manifolds are cobordant if you can get from one to the other by just a sequence of topology changes. Um, and so if you trace out that sequence of topology changes, you build sort of if that manifold you think of as space, you build up a space-time, which is a manifold one dimension higher that traces you from one to the other. So the cobordism conjecture defines charge as equivalence classes of manifolds up to the equivalence relation of topology change. Um, and so the conjecture is that for every such charge, if you calculate this charge, say in the low energy effective theory, and you find a non-zero cobordism class, meaning a horizon that can't be filled in, then your complete theory had better have a new object something in the middle that can fill in that horizon. In other words, something to provide a microstate for that black hole. One example of this is that there's a manifold in every dimension called the real projective plane. It's the quotient of the sphere by the antipodal map. So this is the map that takes each point on the sphere to the antipodal point. You quotient by the sphere by that, you get a real projective n space. Um, and it turns out that in string theory, in type 2 string theory, these manifolds are non-trivial in cobordism. So these manifolds cannot be deformed as a manifold with the structure of type 2 string theory away to nothing. And you could ask, okay, what's the object we need? The object to provide a microstate of a black hole whose horizon is a real projective space. So in 4 dimensions, a real projective plane. Um, and the answer is or what's known as an orientifold plane. So orientifold planes are singularities in string theory that look like a cone over a projective plane. They're sort of you take the projective plane, you shrink it down to a point. That point is a singularity called an orientifold plane. And I think this is actually really exciting because when I was learning string theory, I was confused. Why do we have these orientifold planes? They're this weird thing. Why do we have these space-time singularities and not other, and in particular, not other space-time singularities? Why is this the sort of space-time singularity we have? And the Cobordism conjecture gives an answer. It says, well, you need those because there's a black hole you could write down that would not be able to be made out of anything if you didn't have orientifold planes.
I see. So, correct me if I'm wrong, but this conjecture comes from the no global symmetries conjecture, right?
Directly from no global symmetry. In fact, I think all of these conjectures really are equivalent. So no global symmetries is equivalent to completeness of the spectrum and is equivalent to the Cobordism conjecture. Um, I think maybe in some sense, the most fundamental is the completeness principle.
Mm-hmm.
From different perspectives, you could say one is more fundamental than another.
Sure.
I think that from a modern perspective in the Swampland program, the Cobordism conjecture is one of the most practically useful because it really quantifies what we mean by global charge or complete spectrum. And so it sort of subsumes the others in that there are cases where if you don't use it, you would get the wrong answer for what the global symmetries are. For instance, I had a paper with Matt Reese where we thought about parity. People had in phenomenology had talked about parity strings. These would be cosmic strings. You go around, you pick up a parity flip. And using cobordism, we argue that this is not really a consistent notion.
I see. So, the Cobordism conjecture
Mhm.
says that the Cobordism classes of all these theories is trivial. Is that
Yes.
true? And what does it mean? I mean,
Yeah,
you kind
so
of
so
explained
good.
it.
So I explained what it would mean for a cobordism class to be non-trivial. A cobordism class is
Mhm.
non-trivial if there's a manifold, sort of, if you think of it as a horizon manifold, something that can't be filled in, that would be
Mhm.
non-trivial. Saying that in the complete theory, they're trivial means that everything can be filled in. So if
Right.
you put any horizon, you can fill that in. Um, I think there's another useful perspective on the cobordism conjecture that might be also related to what you're getting at, um, which is that so far I've been describing the manifolds that we're thinking about as the horizons of a black hole.
Hmm.
But there's another thing you can do with a manifold in quantum gravity, which is use it as a compactification manifold. So for theory in some higher dimensions, you can take a manifold, use that to use up some of your dimensions and have the rest of your dimensions remain large. And in that context, when we think about a cobordism between manifolds, if we have a theory, say in 4 dimensions, obtained from string theory by compactification on some 6-dimensional manifold, then as if we take a cobordism from one 6-dimensional manifold to another, in 4 dimensions, that behaves as a domain wall, where on one side of the domain wall you have the theory obtained by compactification on the first manifold, and on the other side you have the theory obtained by compactification on the second manifold.
Hmm.
And so from this perspective, the Cobordism conjecture is the statement that all quantum gravity theories in a fixed dimension are connected, dynamically connected. So if you
Hmm.
have two theories and a dynamical domain wall between them, then you should think of them as two vacua of a single theory.
Hmm.
Um, these are not completely independent physics systems. These are just, well, this is one configuration you could have, this is another configuration you could have. From that perspective, the cobordism conjecture is the triviality of the cobordism classes of quantum gravity is the statement that all quantum gravity theories are connected. In the other sense, that there really is only a unique single theory of quantum gravity.
So let me understand this compactification example. So suppose that you compactify on some Calabi-Yau manifold, right?
Mhm.
And on one side of the domain wall, you have a Calabi-Yau manifold with
Mhm.
some values of the moduli, and
Sure.
on the other hand, you have some other values of the moduli. So they will be connected, for example, by a
So
domain
that's a
wall.
very simple example where this is
Mhm.
those two are certainly connected. Moduli, right, are just the fields which control the shape of the geometry. And of
Yes.
course, I could have the geometry be one shape over here, and then as I move, deform and be the other shape over here.
Right, right, right.
This is sort of a very simple example where the domain wall in the lower dimensional theory, you have moduli fields, and the moduli field would just sort of have a profile where on one side it takes one value and then it moves, and
Yeah,
on the other side it has another value.
sure. But let's take a more complicated example. So
Hmm.
suppose that you compactify on a six-dimensional
Hmm.
Calabi-Yau manifold,
Hmm.
and we do know that if you start from heterotic theory, for
Hmm.
example, you get four-dimensional n
Hmm.
equals one four-dimensional
Hmm.
supersymmetry, right? But if you compactify on a six-dimensional torus, we do know that tori don't break supersymmetry.
That's right.
So on the other hand, if you have a torus compactification, they would still be connected,
The
although they have
conjecture
different.
would be that they would still be connected.
Okay.
The way that those could be connected is it's perfectly consistent to have a domain wall where on one side you have some supersymmetry, the other side you have, say,
Yeah.
more supersymmetry, and the domain wall might break some of the supersymmetry. There's no problem with that.
Right.
Supersymmetry is a property that, you can have in one place and you can break in another. That's totally fine.
I
Um,
see.
One thing to say, though, is that one of the reasons why the Cobordism conjecture is powerful, is that it gives us control without supersymmetry. So
Hmm.
usually in string theory, we really rely very heavily on supersymmetry. Um, I don't think supersymmetry is really fundamental. Well, low energy supersymmetry is not fundamental to string theory. There's lots and lots and lots of vacua, or at least configurations of string theory, maybe not vacua, but at least configurations of string theory that don't have supersymmetry at low energies.
Hmm.
Um, Supersymmetry is just a very useful calculational tool. It makes the math much easier.
Sure.
Basically,
I mean, there are.
supersymmetry. Sorry?
Sorry. I was just saying that there are non-supersymmetric string theories.
There are also string theories that even just in 10 dimensions are not supersymmetric.
Mhm.
I saw actually you have a paper recently on the
Yes.
016 string.
Right.
Um, Yeah, so the reason I would say supersymmetry is so useful is that it, makes a bunch of terms cancel, and so the
Mhm.
calculations are easy. And a consequence of this is that in string theory, the examples where we really have strong calculational control are of two kinds. So either we
Mhm.
have supersymmetry, especially a lot of supersymmetry, or we have weak string coupling. So if the string theory is perturbative, then even if we don't have supersymmetry, such as this example of O16 non-supersymmetric string, the reason why we have some control there is because it's weakly coupled, or at least we have control at weak coupling. Um, One of the benefits of the Cobordism conjecture is that it's totally topological. It says nothing about supersymmetry. And so one of the things that you can use it for is to predict new non-supersymmetric objects. If you
Mhm.
have some configuration, you need to fill it in. The new object you need to fill it in some cases, you can show must break supersymmetry. And so this leads to predictions of new non-supersymmetric objects in well-known string theories. I think that's one of the more exciting aspects of it, at least from the perspective of trying to sort of flesh out the string landscape.
I see. So let's stick to this example because
Sure. Yeah.
just as a placeholder. So
Mhm.
suppose that you have Calabi-Yau's three-fold compactification on one
Yes.
side and a T6 compactification on the other side. So you said that the conjecture says that they will still be connected by a domain wall.
Yes.
So does it? I don't know if it implies that, but does it mean that this domain wall may be a new object that breaks some supersymmetry but doesn't break?
Certainly. I mean, I need to think about that particular example
Mhm.
a little bit more, whether there's
You can take
any
a
of,
simpler example if it
sorry?
helps. You can take a simpler example if
Yeah,
it helps.
that example, I think it may be even just at the level of geometry, you can connect those. There
Hmm.
isn't really an obstruction. The obstruction would be supersymmetry. You can't connect them while preserving supersymmetry.
Hmm.
But at the level of geometry, I don't think there's actually any problem with just connecting them without supersymmetry in that example. Um, Maybe another example would be. let's just take maybe an example related to R7 branes, which is that we could have a compactification. Um, we could have a compactification on, say, a circle, where on one side we have the circle having a supersymmetric spin structure, meaning fermions are periodic going around the circle. And on the other side, we have the circle with a non-supersymmetric spin structure, where the fermions pick up a sign when they go around. And saying
I
that
see.
these two are connected would predict a new object, which would be, in that case, would be a what you might call a vortex for fermion number. It would be a cosmic string. You go around and fermions pick up a sign. So that one can actually, in many cases, be supersymmetric. The one that will not be supersymmetric is what we call an R7 brane, which is where on one side we would have string theory has type 2 string theory has a Z2 gauge symmetry called called -1 to the FL. This is the fermion number of left movers on the string world sheet. Um, in fact, this is kind of like charge conjugation. This is kind of like Alice electrodynamics. This acts as charge conjugation on all of the D branes. Um, and if you take a circle where you have a non-zero, where you have a you put a non-zero holonomy, meaning that when you go around, all the D branes flip to anti-D branes. Then on the other side, you don't put that. The domain wall connecting those would need to be an R7 brane. You would need to, at some point on the circle, put an R7 brane. This is an object defined by the property that when you carry any D brane around it, it picks up a sign. And this
Hmm.
object is non-supersymmetric. We argued in a recent paper that it's stable. So this is a new non-supersymmetric stable 7 brane in type 2 string theory. That yeah.
I see. So, this domain wall connecting like two compactifications can, correct me if I'm wrong, but isn't it true that someone can do like a Coleman-Delucia like calculations with
Mhm.
these, by having like quantum mechanical instabilities,
Yeah,
with
you
domain?
could try to do something like that. I mean, for that sort of calculation, you would need to also know things like the tension of the object.
Yeah.
And this is something that the Cobordism conjecture does not give. Um, there was a recent paper of my advisor Kamran and some students. I think it was Sanjay and Khan, but I may be misremembering who was on this paper. Um, where they gave the following criteria. They said that the objects predicted by the Cobordism conjecture should have sub-Planckian tension. So their tension should be at most Planck scale, which I think is a very reasonable
Yeah.
expectation. I mean, sort of the Planck scale might be the smallest or related to the smallest scale you might have a black hole. And so you could
Hmm.
build sort of the smallest black hole with that Cobordism class and ask that that black hole correspond to an object. So it's sort of
I see.
brain. Um, but yes, for calculations like Coleman-Delucia, I'm talking about having a domain wall between two vacua. You might want to ask what is the tunneling rate
Hmm.
between two configurations. What's the tunneling rate? What are the energetics of these objects? The Cobordism conjecture does not directly give you that. So it's sort of a
Right.
trade-off. You get good control of the kinematics and bad control of the dynamics.
I see. So, one question that I have is that, so correct me if I'm wrong, but if you have a non-commutative space-time, right,
Mhm.
that is not topological. It's not a topological space, right?
It is not a no, it is not a top. Well, you shouldn't think of it as a topological space. There's ways to
I
think about
see.
non-commutative manifolds in terms of a topological space with some structure on top of it that realizes the
Yes.
non-commutativity. But I think it's better to think of them as something different than a topological space.
Sure. So, does Cobordism conjecture apply to non-commutative spacetimes?
So I would say that in general, the Cobordism conjecture applies to the configurations that are part of your quantum theory of gravity. So if your quantum
Okay.
theory of gravity has non-commutative spacetimes as a valid configuration of the theory, then yes, it should apply to those too. Um,
Hmm.
we know string theory in certain contexts can have non-commutative behaviors, non-commutative spacetime behavior. We also know that string theory has non-geometric compactification. So these are
Yes.
compactifications on something. Maybe you can think of it as a spacetime that is very small, and so the quantum fluctuations of the spacetime are very large. In any case, it isn't really well described as just a manifold.
Hmm.
But nevertheless, you can ask when two of those things are connected by deformations. And so
Right.
the same would apply. And there's some really great work by Yuji Tachikawa and a group of collaborators on thinking about cobordism of this sort of thing in the context of heterotic string theory. So their notion of cobordism is that you define the non-geometric space as a worldsheet CFT, and you
Yeah.
define cobordism as deformations of the worldsheet superquantum field
Right.
theory.
I asked that question because when you said that, that Cobordism conjecture is topological, it doesn't mean that it only applies to topological spaces, or does it?
No, no. What I mean when I say it's topological is that it's a kinematic statement. I'm saying that the two
Mhm.
configurations need to be connected in some way. I'm not saying the energetics of the thing connecting them. I'm not telling you it's tension. I'm not telling you things like that. So when I say
Right.
topological, I'm really maybe a better word would be kinematic.
Right. So let's come to this R7 brain thing that we discussed earlier. So my question is that what is R7 brain? How was it like? How was it
Yeah,
discovered? I don't know
yeah.
if
So
that's
this
the correct way
R7
to say
brain,
it.
so this is this brain, it's this cosmic string defined by the fact that when you take a D brane around it, it goes to an anti-D brane
Yes.
for every dimension of D brane. Um, this was discovered by some work of, let me see if I can get the authors right, Jonathan Heckman, Miguel Montero, Arun Debray, Ethan Torres,
hmm
um,
You're talking about Chronicles of Tubordia, right?
Chronicles of Tubordia. I'm missing an author.
Yeah, I think that paper has like 5 to 6 authors, something like that.
Yeah, let
Five
me
or
just make sure I get it correctly. Oh, Marcus Derrigal.
hmm
Um, and so what those guys did, and it's I have a lot of admiration for this because when Cumrun and I wrote this paper on cobordism on the cobordism conjecture, um, we were really focused on, is this true? Is this statement true? Are we doing the right thing? Like, is this are we making a correct conjecture? Um, these guys took this and just bravely went ahead and said, okay, let's believe this. Let's say this is true, and let's go start using it. So
hmm
they went and they did some just heroic calculations. So the way you calculate cobordism groups uses this mathematical technique known as the atom spectral sequence, which is it's really more of an art than a science. It feels like something where the people who are really good at it were apprentices of people who were really good at it. So Arun Debray is one of these people who's really good at it. And so they went and they calculated some of the cobordism groups of the spacetimes relevant in type 2b string theory. In particular, type 2b string theory has an SL2Z roughly duality group. And they
hmm
can calculate the Bordism groups of manifolds with an SL2Z, or more generally, its spin version. Uh, they calculated those Bordism groups, and they found that in every case, the required object was known except one. And the one case where the object wasn't known is this R7 brane. So this is this object you go around and the D branes turn into anti-D branes. Um, the reason they're called reflection 7 branes is that in type 2b has a description in terms of F theory, which is a 12-dimensional description where you have a torus, and this symmetry corresponds to a reflection of the torus. So as you go around, one of the circles traces out a Klein bottle.
I see. I see. So, in one of your recent papers, I think probably in your most recent paper,
Mhm,
you
mhm.
showed that this R7 brain is stable.
Yes.
I mean, we didn't know that earlier. So, can you tell us a bit about the procedure that you used to, show that it's stable, and why didn't we know that earlier?
Yeah, I mean, I think from some perspective, it's maybe clear in retrospect that it would be stable. The 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 stability of this object, I think the history went a little bit back and forth. So Cumrun and I in our paper, we just said, okay, these objects have a topological charge, so they better be stable. And the argument would roughly be that if you have an object of some charge, okay, if it's unstable, it decays to something with the same charge. So just let it decay down to the lightest thing of that charge and call that the object you meant anyway. So that's we thought that they would just automatically be stable. But for objects of low codimension, there's a possibility that we hadn't thought much about, which is that while the charge needs to be conserved, it could spread out in the transverse directions. So if you have like a
hmm
cosmic string here, its energy density of a string would be very sharply peaked in the middle, but maybe it could spread.
Mm-hmm.
Um, the reason why this evades the original argument is that objects of low codimension have such strong gravitational back reaction that when they have different tensions, they actually sit in different Hilbert spaces. They modify the geometry off at infinity. And so you can't just say look for the lightest one because there's no lightest one. They keep getting lighter and lighter and lighter. Um, Part of what's come out of this work of Yuji Tachikawa and collaborators, I think the specific paper is Yonakura and Kaidi are the two collaborators, um, is that if the charge of the object can't be realized by any configuration of the low energy fields, then it should be stable. And the logic of the argument is pretty straightforward. It says, well, if the object is spreading, 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 then its energy density is going down. And if its
Mm-hmm.
energy density is going down, eventually it will be able to be described in terms of low energy fields.
Mm-hmm.
And if you know that there's no way to realize that charge in terms of the low energy fields, then you really need something new and stable. And so that's how that argument goes. And the R7 branes, because they're associated to a disconnected discrete Z2 gauge group, are stable for this reason.
I see. So these R7, so these new objects, one of those objects is R7 brane. Can you have these branes in other dimensions like 6 or 5?
Um, so the R7 brane specifically is a seven-dimensional brane in 10 dimensions. Of course, if you compactify to lower dimensions, you can wrap the brane on some of those dimensions and get, you know, a brane in the lower dimensional theory. I would say the R7 brane is really characterized by its codimension. So the codimension, right,
Mm-hmm.
is the complement of the dimension. And the reason
Right.
is that it's characterized by a property when you go around it. And going around is something about the codimension. It's about the directions
Co-dimension, yeah.
away from the object, not along the object.
Mm-hmm. So
But
if
yes,
if
I would
it
say yes. Yeah.
if it's wrapped on some of the cycles, it's still stable, right?
That is actually not so obvious. That's a really
Okay.
good question. Um, You could ask the same question about the domain wall between type 2A and type 2B.
Mm-hmm.
This is something that Jacques Distler and I have thought a little bit about. So this is, I don't want to say too much because I don't want to give away upcoming work.
Sure.
Um, but it's not entirely obvious that a brain which is stable in higher dimensions will automatically be stable in lower dimensions.
Right. Yeah.
If string theory were automatically geometric, this would be true. So in the regime where the geometry is sort of large and a really good description, this would be true
Mm-hmm.
because if a brain wrapped on something could decay, well, the only way it decays is if it decays somewhere along the wrapping, and then it just decays in the higher dimension. But
I
because string
see.
theory allows things more general than geometry, such as non-geometric processes, it's possible that these branes could become unstable to non-geometric processes that are allowed upon dimensional reduction, but not allowed in 10 dimensions.
Mm-hmm. So that's why it's not that clear, right?
It's not that clear. Yeah. And this is actually a really good question from the perspective, like one thing you might want to do with these R7 branes is use them to build string theory models. Use
Mm-hmm.
them as a source of supersymmetry breaking in a string compactification. This is a big problem in string phenomenology. The world is not supersymmetric at low energies. How do we build models of that in string theory? You need to make a compactification that breaks supersymmetry. Maybe you want to wrap some of these non-supersymmetric branes and break supersymmetry. But the fact that a new instability could appear when you wrap them is something you need to worry about when you want to start using them for model building. So it's a great question, but it's a hard question too.
Um, are you familiar? I'm pretty sure you are. Are you familiar with a Friedwitten anomaly?
Uh, yes, sorry, I'm actually awful with this sort of names. I'm sure I
So
am familiar with the Friedwitten anomaly. Which one specifically is that?
so I think it's about when you compactify, sorry, not compactify, a wrap a D4 brain on a 3 cycle, it becomes inconsistent, something like that. It
If the three, depending on the structure of the three cycle.
Yeah, yeah, yeah. I
Yeah,
think
this
it's
is related to the
probably
fact that
yes.
the gauge
Hmm.
fields on the D branes are spin C gauge fields as opposed to U1 gauge
Right.
fields. Yeah, yeah.
So that would be an example. So correct me if I'm wrong, but I think that would be an example where a stable brain when wrapped becomes problematic.
No, I wouldn't say that.
Okay.
I would say that that's an example where it's not even consistent to wrap it in the first place.
Yes. Yeah,
Uh,
that's why I didn't say stable. I said problematic, right?
oh
It
yeah,
becomes
it is a
problematic.
case where a brain would be where it would be problematic.
Yes.
What I'm talking about is something slightly different where it is consistent to wrap it, it just becomes
Hmm.
unstable. Uh, Let me think for a second. There are examples related to that. So that's one side of the Friedwitten anomaly is
Hmm.
related to the fact that there are some cycles on which you can't wrap a D-brane. But the way that's realized is through what's known as the Atiyah-Hirzebruch spectral sequence for K theory. And so what that tells you, this is a calculational tool that tells you which cycles the branes, for instance, can't be wrapped.
Hmm.
And the way it's calculated is that there's what's known as a differential. Basically, what happens is that some branes, when you wrap them on that cycle, they don't close together. When you try to wrap them on the cycle, they come back with sort of, they're twisted. And so when you try
Yes.
to glue them back together, you're left with some sort of leftover lower brane charge that then has to go off in another direction.
Hmm.
But what that leads to is that if you think instead of the brane coming off in the other direction, then you could view this brane as a instanton process where that one disappears.
Hmm.
And so the flip side of that process is where you would wrap a brane, it would become unstable, which is maybe more analogous to
Right.
what I was talking about.
So, do you have any reason to think that if you wrap R7 brain on some cycle, it becomes inconsistent? Is there any reason to think that?
So there's a good general way to understand when it would be consistent or inconsistent to wrap a brane on some manifold,
Hmm.
which is that branes have world volume degrees of freedom. So for
Hmm.
instance, for D branes, right, you have open strings ending on them, and those provide localized degrees of freedom on the brane.
Right.
Now, the reason it would be inconsistent to wrap a brane on a cycle which is not the technical term, not spin C, um, is if is because it would not be consistent to put those world volume fields on that cycle. It's a
Yes.
manifold on which the world volume fields can't be defined.
Hmm.
The way you would get at the question of what cycles can you wrap R7 branes on is you would want to know what's their world volume theory. Uh,
And we don't know that.
we don't know that. We have some guesses. We can make some sort of guesses using what's known as anomaly inflow,
Hmm.
and sort of symmetry inflow, you might call it. But we don't fully know the world volume theory. It's a question that in principle, you could start attacking.
Hmm.
You could start saying, you know, at least at the topological level, what are the properties of the world volume theory? On what manifolds can the world volume theory be wrapped? Um, and that relates to a question of if you take the new object, you had a cobordism group you calculated before, you get a new object, and you want to include it and recalculate. You want to
Right,
ask
right,
if
right.
you include it, what manifolds do you kill off? And you might also get new manifolds because you might get manifolds that have R7 branes that themselves can't be trivialized.
I
Um,
see.
and to do that, what you need to tell me is you need to tell me what is the structure of the manifold on which the R7 brane lives. And
Right.
for different choices of that, you might get different answers, and maybe there's one that's better or closer to zero or something.
I
Um,
see.
so there's some calculation you could try to start doing. It
So,
would be hard.
oh yeah, I agree actually. So, like D brains have Ramond-Ramond charges, does this R7 brain have any charge?
Yes, so this R7 brane sort of definitionally has a charge. It was defined by its charge.
Hmm.
Um, its charge is the property that D branes going around it pick up go to anti-D branes.
Oh,
And
okay.
so this is sort of one of these generalized notions of charge that comes from the Cobordism conjecture. Um, in this case, it's a sort of more basic notion of charge because you have a Z2 gauge field, minus one to the FL, and
Hmm.
these are magnetic vortices for that Z2 gauge field. So they're the magnetically charged objects for a discrete gauge group. Um,
So, does it have some like flux field associated to it?
the flux field is the discrete Z2 holonomy around it.
Oh, okay,
Yeah.
I see.
Yeah.
So,
And maybe I
so
can say just in general,
mhm.
by definition, the objects predicted by the Cobordism conjecture are charged under the Cobordism class that they're linked by.
Mhm, mhm. I see. So, would you find such kind of, analogs of our brain? So, okay, so correct me if I'm wrong, but this brain was found in the context of type 2 strings.
Yes, I think so. Specifically, it was found in the context of type 2b.
Hmm.
But there's also one in type 2A because type 2A has the
Right.
same Z2 symmetry and the
Sure.
same, you can ask the same question about D branes going around it picking up a sign.
Right. So would you have, analogs of this brain in like O16 cross O16?
That's a great question. So one thing that you should certainly have in O16 cross O16,
Hmm.
um, this is related to the work of UG's that I mentioned before. Um, so they thought have been thinking a lot about analogous branes in heterotic string theory, and
Hmm.
O16 is a heterotic string theory. Um, and one of them is in E8 cross E8 string theory. There's a Z2 gauge symmetry that swaps the two E8s,
Yes.
and so there should be a 7 brane that as you go around it, the two E8s get swapped. And so they've discussed that. But the same should be true in O16 times O16. O16 times O16 also has a Z2 gauge symmetry that swaps the two O16s.
Yes.
And so there should be a 7 brane where when you go around, the two O16s swap.
Right. So if you start from E8 cross E8,
Mhm,
O16 cross O16 is obtained by an orbifold,
mhm,
right?
mhm.
So would it survive the orbifold procedure, the your thing that exists in
Ah,
E8 cross E8? Do we know that?
we don't, I don't know that off the top of my head.
Hmm.
The, I would guess that it would descend under the orbifold to the one that swaps the two O16s. That would be my
Hmm.
guess. But I'm not
I
sure.
see.
The one way you could ask that roughly is you look at the thing you orbifold on the world sheet to go from E8 times E8 to O16 O16, and you ask how it interacts with the symmetry minus 1 to the FL.
Right, right, right. I see. Okay, so another thing that I want to talk about is your paper with some of your collaborators called
Mhm.
Fate of Stringy non-invertible symmetry,
Yes.
right? So there you talked about these non-invertible symmetries that you get when you have tensionless strings. So for the audience,
Huh?
can you tell what tensionless strings are and what these symmetries are?
Yeah, so in string theory, there's sort of perturbative string theory, there's sort of two fundamental scales. So one scale is the Planck scale, which sets
Hmm.
the strength of gravity at long distances, and one is the string scale. So the string scale is the energy or the related to the tension in the fundamental string. In terms of parameters, the string scale is related to the parameter alpha prime, which controls the string tension. Um, Now, the string coupling is related to the ratio between the Planck scale and the string scale. In perturbative string theory, it's natural to work in sort of string units where you hold the string scale fixed and you take the string coupling to 0, which sends the Planck scale up to infinity. Something more physical, actually, I think, from the perspective of low energy physics, is to hold the Planck scale fixed and send the string scale down to 0. It's sort of the
Hmm.
same limit, just in different units. Um, and when you do that, the string becomes tensionless. So the tension of the string becomes very small compared to the Planck scale. So if you work in units where the Planck scale is fixed, then the string becomes tensionless.
Hmm.
Um, this is how it works, at least in flat space. In ADS, the relationship becomes a little bit more complicated, and we have examples in ADS where the string coupling is not 0, but the string tension goes to 0.
Hmm.
So this is one of the examples we considered. So this would be in ADS 5 times, sorry, ADS 3 times S3 times either T4 or K3. Um, there's a limit where you have this would be the system of fundamental strings in the background of a single NS5 brane, where the string becomes tensionless in the ADS space. Um, so the point of that paper was basically that first of all, in the sort of flat space regime where tensionless string means zero string coupling, what we were studying was the fact that non-invertible symmetries on the world sheet, um, because non-invertible symmetries, maybe I can explain it this way. A non-invertible symmetry, as I said before, is a symmetry where you don't just rearrange the degrees of freedom. You take some of them and you throw them out, and then you take new ones
Hmm.
and you add them in. In string theory, when we have string loops, so we go to higher genus in the string perturbation theory, a string loop sort of sends a string state propagating out and then connects it back. And importantly, you only propagate the degrees of freedom you have in a loop. You don't propagate the ones that are over in the trash. And this means that string loop effects break non-invertible symmetries. So the non-invertible symmetry, even if it's valid at the level of the sphere, might not be valid at higher genus. Um, So that was the point of that paper. But we found a very interesting counterexample, which is this ADS string, tensionless string, which nevertheless has non-zero string coupling, manages to preserve the non-invertible symmetry at every order in the string loop expansion.
I see. So you also talk about approximate non-invertible symmetries there. What does that mean?
Yeah, I mean, it's just a general fact that if you have a symmetry and you break it a little bit, then physics still cares about that. If you have, the Earth is approximately a sphere.
Hmm.
Um, it's not exactly a sphere, but it's close enough. Actually, maybe even a better example, the Earth is approximately flat, right? The
Hmm.
Earth is not flat, but the Earth locally is approximately flat.
Sure.
And for a lot of local physics, we can pretend the Earth is flat when we, think about building cars, for instance. We don't need to think about the fact that
Right.
the Earth is round. Um, and so this is just the fact that if your string coupling is non-zero but small, then this effect coming from propagating string loops will be small. And so you might
Right. Right.
expect
Right.
that the physics is still approximately describable in terms of the non-invertible symmetry.
So almost 1 year ago, actually exactly 1 year ago,
Mhm.
because it was 12th December 2024. I mean, as you surely know, because you told me before the recording that you saw this podcast with Zohar
Uh-huh,
Komagowski.
uh-huh, uh-huh.
And one thing that he said is that if a symmetry is violated by quantum effects, we don't call it a symmetry, we just throw it to the trash. So how
Yeah.
is this different from, approximate non-invertible symmetries?
Yeah, I mean, I'm guessing what he was referring to is the
What
concept of a quantum
anomalous?
anomaly.
Yeah.
Um, I'm guessing he probably means what's known as ABJ anomaly, meaning an
Yeah.
anomaly by, yeah,
We were talking about that, yes.
yeah, anomaly by which the symmetry is actually broken, not just sort of modified by background fields.
Right,
Um,
right.
yeah, I mean, an ABJ anomalous symmetry is not a symmetry, but there can be cases where that breaking effect is small. Um,
Mhm. Right.
so I'm guessing the point he was making was that a symmetry which is ABJ anomalous, a symmetry which you call a symmetry at the level of classical physics, but which is broken by quantum effects, is
Hmm.
not a symmetry, of course, is true. But then
Hmm.
you can ask the more refined question of how big are those effects and is it approximately a
Right.
symmetry? Um, in general, actually, I don't think there's a completely invariant notion of which symmetries are broken only by quantum effects and which ones are only broken by classical
Yeah,
effects.
yeah.
This is not really an invariant
I
property
mean,
of physics.
my point was, I mean, I just said it as a joke. You took it way too seriously,
Oh, sorry.
but it's fine. But one question that I have is that so you start with some non-invertible
Huh?
symmetries, right? And then quantum mechanical effects break those symmetries. So and what you're saying is that the effects of the quantum mechanical effects are small, so therefore they are still symmetries but approximately. So can it happen that there may be some other non-invertible symmetries that you don't know and they are still there, but you don't know them because they are approximately broken?
Um, that's possible. What was nice about these ones is that they're exact at zero string coupling.
Okay.
So we know that we know we can go to a sort of limit of a parameter space where we know they're exact.
Hmm.
Um, and so my guess would be that if you have a non-invertible symmetry that becomes exact at zero string coupling, then it should be realized as a non-invertible symmetry on the world sheet. And so we
Hmm.
would have covered it. Yeah. Mhm.
So and these non-invertible symmetries are found in ADS-CFT, right?
Yes, yes. There's a little bit of a there's a little bit of a subtlety, which is that CFTs can well have non-invertible symmetries. This means, by the usual rules of ADS-CFT, that the bulk has a gauged non-invertible symmetry.
Hmm.
But in many cases, gauged non-invertible symmetries can be the same thing as gauged invertible symmetries. Um,
Yeah.
for instance, they might be electromagnetically dual.
Hmm.
And in the cases, almost every case we checked, again, outside of this tensionless string example, the way the symmetry, which is a non-invertible symmetry of the CFT, the way it
Hmm.
becomes realized on the world sheet is as an invertible symmetry. It's through the duality frame in which it acts invertibly on the world sheet. Um,
Hmm.
so there's a little bit of a subtlety when your symmetry is gauged in saying even what your symmetry is, because gauge symmetry is a redundancy of the description rather than a physical thing.
Right. So, okay, so I had another question,
Huh?
and actually a different line of questioning. But
Huh?
since you have mentioned this, let me ask you this. So, I don't know if you have experienced the same thing that I have.
Mhm.
Have you ever felt that people use the word gauge in many different contexts?
Um, I'm not. Maybe you can explain what you mean.
So sure. So I used to think that okay, gauging means in
Yes.
undergrad you were told that gauging means that you make a global symmetry
Yes.
local. Then you
Yes.
were told that well you make the background field dynamical and you
Yes.
sum over all the fields. What does gauging mean?
That's a very good question. So
Right.
yeah, maybe even just a first thing to say is, there's clearly two distinct things that are called gauge symmetries. One is a
Hmm.
symmetry where the symmetry transformations depend on the point in space. I think this is sort of most directly connected to the word gauge, meaning that like you have some gauge that you vary over space, and so you
Yeah.
do different symmetry transformations. This is related, but not really the way that I normally use the word gauge. I use another meaning of gauge symmetry is that it's a redundancy in the description as opposed to a physical transformation.
Hmm.
Um, Maybe a way to think about it in terms of gauge is that it's a symmetry that comes from changing the way you measure things, not the way that the things actually are. Um,
Okay.
that's
Sure.
why it's a redundancy of the description. Um, and in fact, we know these two things are not always the same. So there's
Yeah.
examples where we have global symmetries where the symmetry transformation depends on space-time. So these are things like called subsystem symmetries related to things like fractons.
Hmm.
These are global symmetries, meaning that they transform the system physically,
Hmm.
but they do so in a spatially dependent way.
I see.
And
I mean,
conversely, we could have
yeah.
symmetries
Sorry. Go on.
that don't depend on space-time but are still gauge symmetries. So for instance, discrete gauge symmetries, if you don't sort of have a
Hmm.
lattice model, the discrete gauge symmetry transformation is still really sort of all at once because you can't
Hmm.
like break it. I mean, there's some caveats to that statement, but you can have symmetries where discrete symmetries where really it's not space-time dependent, but still it's a redundancy of the description.
Right, right, right. I mean, when people talk about discrete, well, discrete gauge symmetry, yeah, discrete gauge symmetry, they talk about these network of like, topological, defect
That's right.
lines.
So yeah, so maybe I can say also in the context of non-invertible symmetry, I think it's we have a formal notion of what gauging means, but I think that the physics of what it means is a little bit unclear.
Hmm.
Um,
Yeah.
Gauging is a process by which you take a symmetry which is a redundant, which is a physical symmetry, and you try to make it a redundancy of the description. You try to identify states which are identified by the by the symmetry transformation.
Right, right, right.
Um, and you have to do this when you gauge. You also have to add what's known as twisted sectors. Um,
Hmm.
and the reason you need this is that there's various ways to say it. One mathematical way to say it is that you have to take what's known as homotopy fixed points instead of fixed points, but a
Hmm.
physical way to say it is that you don't just want to know that your state is invariant, you want to know sort of dynamically how it has been identified with itself, and that leads to twisted sectors.
Right, right, right. I mean,
Um,
for example, when you orbifold,
exactly.
under a symmetry, you have to add some twisted sectors, and that's like gauging a symmetry, right?
You have to add twisted sectors, and a physical way to think about why you have a twisted sector is that when you gauge the symmetry, you identified states under Z2, but when you go
Hmm.
around the circle, you have to ask, are they identified the same way or a different way as you go around the Z2? And that's the twisted
Right, right,
sector.
right, right,
Um,
right, right.
for non-invertible symmetry, so this notion of gauging corresponds to modifying your theory by summing over all possible insertions of a network of operators that implement the symmetry.
Hmm.
And you can talk about that notion for non-invertible symmetries just as well. You can ask what are the consistent networks you can insert. You might call these gaugeable or condensable algebras or something. Um, These are the ones where you can insert a network on a manifold, and the answer is invariant under deformations of that network, reconnections of the network, for instance.
Hmm.
You want the answer not to depend on exactly how you put the network in. You want it to be really a sort of invariant process. So that's what it means to be a gaugeable symmetry. And then you can add this network on top of your manifold and define a new theory where you've modified the theory by inserting this network of operators. Um,
Right, right.
but I think the physics of that is not entirely clear. What this is doing. One thing to say is that there's a correspondence between generalized gauging, this notion of gauging non-invertible symmetries, and topological defect operators themselves. So
Mm-hmm.
whenever you have a theory, an engaged version of the theory, there's always a topological junction for discrete symmetries, finite symmetries. There's always a junction between the two, a topological junction between the two, where you say, on this side of space-time, I'm going to put my network. On this side of space-time, I don't put my network. And because the
Mm-hmm.
operators themselves are topological, that boundary condition is also topological. You could call this the Dirichlet boundary condition.
Yes.
Um, but if we didn't know there was a network, we just have a theory on one side, a theory on one side, and a topological interface between them.
Mm-hmm.
And this is called a gauging interface. And the way you can think about that is that as you sweep that interface across space-time, it's modifying the physics by doing the gauging. So an example of this is the Kramers-Vanier non-invertible symmetry of the
Mm-hmm.
critical Ising model in 1 + 1 dimensions. Um, we usually describe it in a very abstract way. We say that there's an operator that implements some symmetry that has this and this algebra. But there's a very physical way to say it, which is that there's an operator that does the following. As you sweep the non-invertible symmetry operator across your space-time, it modifies your theory by gauging Z2. That's what it does. And so that's the sort of operation that takes some degrees of freedom and throws them out. So it throws out the degrees
Mm-hmm.
of freedom that are not invariant under Z2, takes new ones in, goes to the twisted sector, and leaves the theory invariant. So the action of any topological operator can be viewed as a combination of sort of generalized gauging and reorganization of your degrees of freedom, which is an invertible symmetry.
Right, right. So, I mean, there are several ways to see it, but one way to see it is using this domain wall thing that
Huh?
you mentioned. It shows you that you can also undo a gauging, right?
That's right.
Right, which is not something that you learn in undergrad, right? That you can also undo a gauging as well.
Yes, although I would say that there's a very important difference between what we mean by gauging for finite symmetries and what we mean by gauging for
Yeah, true,
continuous symmetries. Because for
true, true, true,
continuous
true, true.
symmetries, you really, well, okay, you can kind of undo. I would say in maybe in graduate school, but you do kind of in some
Hmm.
sense learn that you can undo gauging in the following sense. Um, it's what's called Higgsing.
Yeah, true.
When,
Okay.
when, when you have a gauge symmetry, right? A
Hmm.
gauge symmetry again is a redundancy of the description.
Hmm.
Higgsing means you add an additional field, which sort of serves as a pointer to point in some direction, and that freezes out the gauge field and lets you again talk about the non-gauge invariant fields you had before. Um,
Right.
for discrete symmetries, this is more of an exact thing where really you gauge and then you ungauge and you get back where you started. Um,
Hmm.
But there is an important sense in which ungauging isn't quite the in. This is why they're non-invertible. Ungauging isn't the inverse. It's more of like the reverse. It's like doing it in the
Yes.
opposite direction. The reason is that if you have your system, you take some degrees of freedom, throw them in the garbage, grab some new degrees of freedom, add them in. Ungauging is taking those new degrees of freedom you added and throwing them in the garbage, and taking yet a third degrees of freedom and putting them in. And the
Right,
reason
right,
it's
right.
not invertible is that you don't actually get back the degrees of freedom you threw in the garbage in the first place.
Yeah.
You sort of get a replacement for them.
Right.
And this is the statement that the fusion of gauging and ungauging interfaces is a projector onto the gauge invariant ones. It just only preserves the ones you never threw out, never added in, but the ones
Hmm.
you threw out still get sent to zero under the action of gauging ungauging.
Right, right, right. Okay, so one more thing that I wanted to talk about is actually another swampland conjecture that you have
Uh-huh.
worked to some extent. It's the weak gravity conjecture. So,
Uh-huh.
and there are many versions of weak gravity conjecture,
Yes.
like lattice weak gravity, and then
Yes.
for branes and things like that.
Mhm.
So, for the audience, can you tell what the weak gravity conjecture is?
Yeah, so the weak gravity conjecture, so we talked before about the sort of completeness hypothesis, the principle that for any sort of any charge, you need a state. The weak gravity conjecture makes that uh, more quantitative. It says that if you have a continuous gauge field with some gauge coupling, like the electromagnetic coupling or the strong coupling, um, not only do you need a charge state, but you need a charge state that's sufficiently light. In particular, you need a charge state which has more charge per mass than a very large extremal black hole. Basically, when you have a charged black hole, um, there's a maximum amount of charge per certain mass. And the reason is that if the charge gets larger than the mass, there's various ways to say it, but basically the electromagnetic field can get so strong that it lets you actually get in and out from the singularity. There's maybe one way to say it. Um, the weak gravity conjecture is a statement that there's a particle who has a larger charge to mass ratio, more charge than mass, than that limit for a very large black hole. Um, maybe another way to say it that might be more connected to what we've been discussing is that I said that having a charge is related to the breaking of one-form symmetry, saying that the field lines can end. Weak gravity conjecture quantifies how badly broken that symmetry is. Again, we were talking about approximate symmetries before. So this is saying that the symmetry needs to not just be broken a little bit, it needs to be broken a lot. So that's the weak gravity conjecture.
Sure. So then there are many versions of it. For example, there is a version which is called the weak gravity conjecture for branes, and then there
Yes.
is lattice weak gravity, and then there
Yes.
is convex Hull scalar weak gravity
Yes.
conjecture. So
Yes.
what are these three versions? How are they different?
So maybe one thing to start by saying, this is a point that my collaborator, Irene Valenzuela, likes to make, is that really there's only one thing, and that one thing is whatever the correct version of the weak gravity conjecture is. The reason why we have this like proliferation of conjectures, I think this is something from outside the Swampland program sometimes seems a little bit annoying or like, why are they doing this? The reason why we have so many conjectures and why we sometimes give them names is just because we need to talk about them and we need to, what we're trying to do is we're trying to understand what is the correct statement. And so we're trying to pin down which of the various ways you could really make the statement is the right one. But I can explain what these examples are. So for instance, the lattice weak gravity conjecture is the statement that you don't just have one state, or the sublattice version, you don't just have one
Hmm.
state, but you have a whole tower of states, or even you have states at sort of evenly spaced charges that satisfy this property that have more charge than mass.
Hmm.
Um, the one for branes says that, okay, not only should you impose this for particles that are charged under a continuous gauge symmetry, but also for strings and membranes that are charged under a continuous gauge symmetry. And the logic for that is almost essentially the same.
Hmm.
Um, it gets worse if you want to talk about the weak gravity conjecture for instantons. That one is a little bit harder to justify from first
Right.
principles. But and then things like the scalar convex hull weak gravity conjecture. These are that one is maybe more of a statement that's analogous to the weak gravity conjecture. One way of saying the weak gravity conjecture is that there are particles so that they're such that their electromagnetic repulsion is stronger than their gravitational attraction. And the scalar weak
Hmm.
gravity conjecture is related to a statement like that, uh, where the force we're talking about is not electromagnetic force, but force mediated by a scalar particle, like a Higgs
Hmm.
Yukawa interaction or something like that.
I
Uh,
see.
maybe not Yukawa exactly, but some sort of scalar mediated interaction.
Hmm.
Um, but I do want to emphasize, I think that really what's going on is that there's some correct statement, and we're trying to figure out what is that correct statement. Um, and to avoid every time you say something saying the conjecture that this property that that for every scalar there is a state such that blah 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 blah. It's just easier to say the scalar weak gravity conjecture or
Sure,
something,
sure.
just for ease of discussion.
I mean, just to make it clear, I like those conjectures. I'm
Yeah,
just
yeah,
asking for other people.
I'm aware.
Sure,
I know that there are people out there who will say,
sure.
"Oh, these swampland guys, why are they just making conjecture after conjecture after
Oh
conjecture?"
yeah, yeah, yeah. I mean, the thing is that if you say that these are conjectures, isn't that humble? You can say that these are
That's
statements,
my
right?
perspective. That is my perspective. I think that a lot of theoretical physics involves conjecture. I mean,
Sure.
in fact, in my own background, I was split between whether I wanted to go to physics grad school or math grad school.
Hmm.
And I'm very happy I chose physics. I still use a lot of math in my research. I'm very interested in a lot of math. But part of the reason I did that is that I think a lot of the interesting questions in physics are the ones where we can't say something precise because we
Hmm.
don't know. Because it's hard, things like quantum gravity, where we can't make sharp statements because that's the problem, is we're trying to figure out how we can make sharp statements. So I think a
Right.
lot of theoretical physics involves conjecture.
Hmm.
And I think that yes, I think that it is humble to say it's only conjecture. I think you could worry about taking the conjectures too seriously as opposed to understanding that they are conjectural. Um, various different conjectures have different level of support. Something like no global symmetries, honestly, I think we shouldn't even really call a conjecture. I think that we have so much evidence for it at this point. And more the problem is that I don't even think we really know what, maybe I can put it this way. If we found something that looks like quantum gravity but has a global symmetry, we might say, well, that's not really what we meant by UV complete quantum gravity in the first place.
Yeah, so
Um,
that's in the swampland.
but it's not that it's in the swampland. It's just I don't even know how to think about what it would mean to have holographic quantum gravity with a global symmetry.
I see. I
There's a
see.
very nice paper of Dan Harlow and Hiroshi Oguri where they formalize this argument for no global symmetries from the holographic principle. It's a very nice argument, and their paper became very long. And from talking to them, part of why it became long is because people would keep picking holes at their argument. They would keep saying, "Well, why are you saying it this way? Why are you saying it this way?" And part of the problem is that what they were trying to do in that paper is define a straw man. They were trying to define what it would mean to have a global symmetry, so you can rule it out. And the problem is that there isn't a good notion of global symmetry in holographic quantum gravity. So this one, for instance, I would say maybe shouldn't even be called a conjecture. It's if you call that a conjecture, you should call holography a conjecture, which maybe you should. But in any case,
Sure.
I think those are sort of equal level of conjectural. Um, things like the weak. There's a plot that Hiroshi likes to draw where you have two axes. On one axis, you have level of theoretical support, level of rigor for swampland
Hmm.
conjectures. On the other axis, you have uh, utility for say phenomenology. And the
Hmm.
conjectures you plot them, they all kind of go like this. So the ones which are really rigorous are the kinematic, qualitative ones that aren't so useful for pheno, and the ones that would be very useful for pheno if true are much harder to justify from first principles. Um, yeah.
So this paper that you're referring to, is that like the 2018 paper?
Yes. Yes.
Oh, I think that, so I should say one thing. So that paper is the most careful paper when it comes to the words like gauging and things like that.
I think that
They
paper is
find those
very careful. That paper is very,
very,
very
very
careful. They
careful.
worked very hard to be very careful. And again, the reason they worked very hard to be careful is that if you really want to say you've proved something, you need to
Yeah.
sharply define what you mean. And when you're
Right.
trying, it's somehow much harder to prove that something doesn't have a property than it does, right? Because what we're
Yeah.
they're trying to prove that there isn't something you could call global symmetry in quantum gravity. And that's a hard thing to prove. You
Mhm.
can call whatever you want. So they gave a very sharp notion of what it could mean to have a global symmetry in quantum gravity and argued against that. And so that paper is very, very careful.
Let me tell you something funny.
Yeah.
So recently I wrote this article with two of my friends. So I'm a bit interested in theories of consciousness as well.
Uh-huh. Uh-huh.
And especially rule out those things which have nothing to do with physics. So there is this
Sure.
thing called panpsychism, right?
Uh-huh. Uh-huh.
Panpsy you know about that?
I think roughly, yeah, but maybe
So
yeah.
sure. So just to cut it short, panpsychism says that that consciousness is like a fundamental property, like
Uh-huh.
charge,
Uh-huh.
right? So
Uh-huh.
everything is conscious, just to but human beings are very conscious because they have too much
Uh-huh.
of it. So I asked this question that okay, so if consciousness is so in that article literally wrote this that if consciousness is like charge, then
Mm-hmm.
is it if it's a global charge, then does
Mm-hmm.
it survive at the Planck scale, for example? And if it does, then it violates the no global symmetry conjecture.
You know, okay, so I can maybe I can say, I think I've said enough overly technical things in this podcast that I can
Sure.
veer into this direction without sounding like too much of a crackpot. Um, but I think that there's a sense in which what you just said is related to another swampland conjecture that I view as equivalent to no global symmetries, which is the
Hmm.
one-dimensionality of the closed universe Hilbert space.
Oh, yeah, yeah, yeah.
So this is a very interesting idea that has been, I think, gaining more and more traction. One way to phrase it is that quantum information entropy in quantum gravity is a gauge charge, meaning that the
Hmm.
net entropy in a closed universe is zero. And in an open universe, the net entropy is all contained on the boundary, which you could call Gauss's law for, you could say the holographic principle
Yes.
is Gauss's law for entropy.
Mm-hmm.
And this has led to people starting to think about things like the observer and trying to understand really what is the observer's role in quantum gravity.
Mm-hmm.
And if you want to start asking questions like, what is consciousness? Is it emergent or is it fundamental? The word consciousness is overloaded, of course. Um, there's the sort of active processing that we do, which is one thing. And then there's also the sort of experience of qualia. We stare out at the universe and we experience things happening. And I think we're really talking about the second one. Um, then the statement that there are no net degrees of freedom in a closed universe is in some sense a Gauss's law for the consciousness in the closed universe, if you want to put it that way.
I see.
Um, I think that this is the sort of stuff that's going to make me sound like a crackpot.
No, no.
Um, but I think that we're learning that in quantum gravity, you have to take seriously something we've known about quantum mechanics the whole time, which is that
Mm-hmm.
in quantum mechanics, you should not treat yourself quantum mechanically. You should say, I have a system under study,
Mm-hmm.
and I, the observer, is sort of a first principles notion in quantum mechanics. You can try to approximate it, but it's the thing that's measuring the observables on the system.
Mm-hmm.
And no, most of the time, when we think about the relationship between the observer and the system, we can kind of forget that the observer is there. Because for most
Mm-hmm.
quantum systems, we can all be the observer at once. Because, like, when you have a quantum field theory, it's like it's sitting on a lab table and we're all looking at it.
Right, right, right.
But
But in
in
some
gravity,
interpretations, yeah.
sorry,
Sorry, but in some interpretations, like the manuals, the observer is quantum mechanical.
my personal perspective is that
Yes.
what we're learning about quantum mechanics in a closed universe is inconsistent with many worlds.
Okay, I
Um,
see.
what we're learning the reason why this is modified in quantum gravity is that in quantum gravity, the observer is connected to the rest of the universe by gauge constraints, by gravitational gauge constraints.
Mm-hmm.
Um, what this means is that different observers in quantum gravity might have access to fundamentally different descriptions of the physics. So an old instance
Mm-hmm.
of this is for the infalling observer falling into a black hole. So there's an old idea of
Okay.
complementarity going back to Susskind, where you might have one quantum mechanical description for the observer falling into a black hole and a different
Mm-hmm.
one for the observer who stays outside. And all that physics requires is that if somehow those observers sometime in the future meet, maybe the external observer collects all the Hawking radiation and reconstructs them using quantum error correction, that they agree, that they say things that are consistent.
Mm-hmm.
But this, I think, is not compatible with many worlds because, as I understand many worlds says that there's one Hilbert space. That's it. That's quantum mechanics.
That's
And
true.
and I think what we're learning in quantum gravity, at least from my perspective, is that if you want to talk about physics behind a black hole horizon or in a closed universe, there isn't one Hilbert space. The Hilbert space is as subjective. The Hilbert space is subjective. The wave function is subjective. But again, I think this is something that's really always been there. When you talk about here's an example where the Hilbert space is subjective. Let's say I'm
Mm-hmm.
talking about, you know, uh, simple harmonic oscillator, and you're talking about the hydrogen atom.
Mm-hmm.
Those are different Hilbert spaces. They have different
Yes,
Hamiltonians, different operators.
sure.
It's not surprising that those are subjective. You're looking at a hydrogen atom, I'm looking at a harmonic oscillator. These are different
Yes,
systems.
right.
It's just that in quantum gravity, it seems that when you try to think about the whole universe as a system, you get a trivial answer.
Yes.
So you're forced to think more carefully about which part of the universe is system, which part of the universe is observer.
Okay, I see. So, do you think that something like so there is another interpretation of
Mhm.
quantum mechanics called cubism? Do you think that that's more it's closer to what we are learning?
I think that that is more compatible with what I'm
Okay.
with quantum gravity. It's funny. This is not something I'm an expert on at all, but
Mm-hmm.
I have never understood exactly to what degree cubism is different from Copenhagen. I,
Well, the difference is that probabilities are, subjective there, but in Copenhagen they're not.
Well, but what if you're a Bayesian who learns Copenhagen?
Sure, but then you're a cubist, right? You're not
Maybe. You can quibble about semantics,
sure. Okay.
but yes, I think what I'm saying is that, at least from my perspective and the perspective of trying to understand observers falling into black holes or enclosed universes, you're
Hmm.
forced to view the Hilbert space and the wave function as subjective. And I think you always should have, but you can get away with not thinking that way outside of the context of quantum gravity.
So since we are talking about this,
Yeah.
let me throw another idea there. It may be again
Mhm.
we're very much out there, but so I'm sure you know about -1 form symmetries,
Uh-huh. Uh-huh.
right? So -1 form symmetries like connect different Hilbert spaces. So do you think that these subjective Hilbert spaces may be connected by a -1 form symmetry?
Minus one form symmetry, I mean, it's something that I've written about in a number of papers. It's a little bit, in some sense, I think the naming is a little bit tongue in cheek. It makes it sound like there's something really fundamental. A
Yeah.
minus one form symmetry is just a parameter.
Yes.
It's not like something more deep than a parameter,
It's like
something
the
you
theta
tune.
parameter, right?
Sorry?
Of it's like the theta parameter in
Yeah,
Yang-Mills
yeah,
theory.
but also like there's different perspectives, but I would say also like the gauge coupling, also like the electron mass, also like the electron Yukawa.
Sure.
Just from my perspective, a minus one form symmetry just means a parameter. Um,
Right.
it doesn't
But
need to be a parameter with any sort of topological nature or well, this is maybe up to debate.
mhm,
Um, what I would say is that yes, I would say that when you want to talk about an observer or quantum mechanical system, there's choices to make. For
mhm,
instance, you could say, you need to choose which measurements the observer can make. And these
mhm,
are some form of parameter. A more simple example is in context of ADS CFT. In some sense, you can view the entire ADS boundary as one big observer who's sitting at the boundary of ADS and can measure anywhere at the boundary.
mhm.
Um, then parameters of the CFT, like the theta angle, correspond to parameters of that boundary condition, things like the asymptotic value of bulk fields. Um,
Yeah.
and sure, yes, as you tune those parameters, you get different Hilbert spaces with different representations, maybe, or even operator algebras. Um,
Mhm.
and so, yes, I would say that as you change the parameters of a quantum mechanical system, you're changing the way in which the observer can interact with the system. Um, you could also view it as
Sure.
changing the system, of course, but there's some sort of complementarity between those two
I
things.
see.
Yeah.
Okay. So let me come back to what we were talking. So
Mhm.
we were talking about
Yeah.
no global symmetries conjecture, right?
Yes.
Um, so sorry, we were talking about weak gravity conjecture. So
Mhm.
I mean, when we were talking about the completeness of spectrum conjecture and the no
Mhm.
global symmetries conjecture, we discussed which conjecture is fundamental or are they independent, right?
Uh-huh.
So
Uh-huh.
is the weak gravity conjecture independent of the other two that we discussed?
I would say that the weak gravity conjecture um, is a refinement of the completeness conjecture or completeness hypothesis. Um,
I see.
maybe actually one thing, sorry, just a side comment.
Hmm.
We were talking before about the name of these things for conjectures. I even think conjecture is maybe not even the right name.
Hmm.
And the reason is that, from my perspective, a conjecture is a mathematically precise statement that is either true or false in some framework. And I would view that these swampland things as not even conjectures. The reason they're not even conjectures is that we don't have a precise definition of quantum gravity. So I
Okay.
might call them, I think hypothesis is really a better word. They're physical hypotheses. They are, it's the scientific method. They are guesses about the way gravity works that may or
Hmm.
may not be true.
Or we can put conjecture in quotes.
You could put conjecture in quotes. I think I like the word hypothesis. Anyway, some of the conjectures just
Sure.
historically you call hypothesis. So like I would typically say completeness hypothesis and
Hmm. Sure.
whatever. Completeness hypothesis. So I would say that the weak gravity conjecture or weak gravity hypothesis um, is a refinement of completeness. So in particular, the weak gravity conjecture implies completeness because if you insist that for every charge there's a state that's sufficiently light, you've certainly imposed that for every charge there's a state.
Hmm.
It depends on the version. Maybe the sublattice or the yeah, it implies some weak version because it might not imply every site on the lattice has a state, but they're
Hmm.
closely related. Um, but it's
So,
definitely stronger. It's definitely not. Okay, maybe I shouldn't say definitely, but it's without some sophisticated argument. I don't see a way to conclude weak gravity from absence of global symmetries.
okay, I see. So, let me take something like, the statement that you don't have interacting conformal field theories in more than six
Mhm,
dimensions.
mhm, mhm.
That is a conjecture because that's a very like
That I would call a
precise
conjecture.
statement.
Yes, exactly. That I would call a conjecture. I mean, maybe a mathematician wouldn't even call it conjecture, but I think at the
Sure.
physics level, that is a well-defined statement that presumably is either true or false.
Hmm. Okay, I see. So one more thing that I want to talk about is something called the distance conjecture, because
Huh?
there are many different kinds of different conjectures, and
Definitely.
people are talking about like, are they satisfactory? Although
Mhm.
they have a lot of evidence for them as well. So can you tell us a bit about what is the OG distance conjecture, and then what
Yes,
are the
yes,
other
yes.
versions
So,
of distance
the
conjecture?
the original distance conjecture. In fact, Qumran sometimes says that he wishes he called it duality conjecture. Um,
Sure.
the distance conjecture is the statement that as you move to asymptotically far regions of parameter space or configuration space in quantum gravity, you should get a weakly coupled tower of light states coming down and becoming lighter and lighter compared to the Planck scale.
Hmm.
And the reason you might call this duality conjecture is that the interpretation is supposed to be that as you get into that asymptotic region, a new description of the theory takes over, where the states that are becoming light are a new perturbative weakly coupled description of the system. And this we see this all the time in string duality. Maybe you start at one side of parameter space in terms of one description of the theory, and then as you go across parameter space, as you end up in the other region, you find that different degrees of freedom are light, and those are a better description of the physics at that end of the moduli space or field space. So the
Sure.
original distance conjecture is precisely a statement about supersymmetric moduli spaces. It's a statement that when you have a supersymmetric moduli space of string vacua, that this is true. That as you go to very far to a corner of the moduli space, that this happens, that you have light states coming down and a new dual description opening.
Hmm.
That is the one that has the best support from examples, just you could call it circumstantial or you could call it, evidence based. You look at the set of string vacua and you just check if this is true. That's the one that has the most support. Um, one of the big questions is to what
Sorry.
degree does the distance? Oh, sorry.
So,
Yeah,
sorry, let me ask one question
yeah,
before you proceed. So you
please.
said that this one has the most support. So do we have top-down support or bottom-up support?
Um, maybe if by top down you mean
So you
checked
start
in
from some,
examples of string theory,
yes.
yes, then yes, this is one that has tons of top down support.
Okay.
Um,
What about bottom-up?
Bottom up, I don't think there's a really, really convincing argument, sort of from first
Okay.
principles of quantum gravity, why this should be true.
Okay.
Um, there's things to say. I mean, one thing that I like is this idea of sort of the finiteness of quantum gravity. There's a
Mm-hmm.
paper of Cameron, Miguel, and Irene on this, on finiteness of quantum gravity. Um, the idea being, again, that the entropy in a finite region in quantum gravity we expect to be finite.
Yes.
And one way you can think about the tower of states coming down is that any fixed effective field theory, say with a cutoff energy scale, should only have explore a finite amount of moduli space. So it's a fact that moduli spaces have these infinite corners where you can go off infinitely far away.
Mm-hmm.
But if a tower of states comes down, then they come down under your effective field theory cutoff. And so there's a maximum distance in the field space you can go while staying in a single effective field theory.
Yeah.
So that's sort of a bottom-up motivation for the distance conjecture.
Mm-hmm.
This is certainly less sharp than the arguments from black holes for no global symmetries, for instance. But I think it's
Sure.
a good intuition as to why the thing should be true.
Okay. So yeah, you were saying, I asked you a
I was going
question.
to say one big question is to what degree the distance conjecture extends outside of the context of supersymmetric moduli spaces.
Yes.
Something that's been checked a lot is cases, say, with n equals 1 supersymmetry in 4 dimensions, where you could describe it in terms of a moduli space, but really you get a superpotential and the moduli space gets lifted. And so you don't actually
Hmm.
have an exactly flat moduli space. The distance conjecture has been checked to in many examples of this form. There's lots of evidence that it's true in this context
Hmm.
too. One very exciting direction is whether the distance conjecture applies to sort of more abstract directions in field space, such as the cosmological constant. So one
Hmm.
direction in field space is taking the cosmological constant to zero. The natural metric on the cosmological constant uh, actually has zero at infinite distance. The reason roughly is that if you have just a manifold with some curvature, say a sphere, as that sphere becomes the plane, that's sort of infinitely far away from the sphere. Uh, One way to say it is that the metric sort of is natural, like the logarithm of the curvature is more naturally the sort of distance scale,
Yeah.
um, or the thing that is naturally sort of parameterized. Um, what this would imply, for instance, is the fact that the cosmological constant in our universe is so small, then there should be some new dual description opening up. And this is what the dark dimension that Cameron, Miguel, and Irene proposed, which I think is a fascinating idea. And I really do think is a good test of the validity of this very general notion of distance conjecture. I think
Hmm.
there's overwhelming evidence that distance conjecture is true in supersymmetric moduli spaces. If we find, and one thing that's nice about the dark dimension is that we're going to know. The sort of fifth, fourth experiments to check if there's a dimension 60 microns, roughly 60 microns, somewhere in that order large. Those are going to be done in the next, I don't know exactly, but 10, 15 years. And we're going to
Hmm.
know. We don't have to argue. We can just wait to see
Yeah.
what we find. And I
Right.
and I and I think that I think it's worth saying that comes if that isn't true, then we do need to be more careful about the general form of the distance conjecture. Because
Hmm.
I think the logic that they use to get there is very strong, given that the distance conjecture applies to the cosmological constant. Of course, it's
Right.
possible that it doesn't. But given
Sure.
that logic, I think the chain of logic is very strong.
I mean, this the dark dimension thing. So, I mean, I don't work in dark dimension, but I have been following it. So I think it came in 2022, if I'm not wrong, right? Something like that.
Something like that, yeah.
Yeah. So I was like, okay, it's a good idea. But no, not last year, this year, when I was at Simon, I was blown away by a talk given by George Zubaid. I mean,
Yes.
he gave this talk about, how can you achieve, phantom dark energy when none of the things that you have W less than -1. I was like, okay, that's like magic. And
Mhm.
that comes out of dark dimension. So yeah, I was very excited about that
It's
talk.
it's it's the work George has been doing is very, very exciting. I mean,
Hmm.
it what I'll say, like the sort of numerology is good. The when you say you have an extra dimension and then you say, okay, so then there will be extra dimensional KK modes. These are naturally things that don't interact with the standard model matter very strongly, but would be populated as the universe
Hmm.
cooled. I mean, and that would be dark matter. I mean, the numerology seems to be very good. Um, I'm not a phenomenologist, so I really am not. I can't evaluate, to what
Hmm.
degree, Georges, for instance, knows much better about how this actually connects
Yeah.
to known facts
Right.
about cosmology. Um, but I mean, it's a beautiful picture, and I think that no matter what your perspective on the conjectures that lead to it, I think it's something worth being excited about.
Right.
Um,
Right. Right.
at Caltech, I recently moved from Caltech. I finished a postdoc there. Now
Hmm.
I'm here at the Simon Center. And John Schwartz, of Green-Schwartz mechanism
Yeah.
of string theory fame, was very, very excited about this. And he indicated that, you know, he always wanted string theory to connect to the real world.
Sure,
As
he
many
is
of
one
us
of the
as many of
pioneers.
us have. Yes,
Right.
and so it's very exciting. I think it's worth emphasizing that if this is wrong, then string theory isn't wrong. This isn't a test of string theory. This is a test of a very particular
Mm-hmm.
corner and extrapolation from string theory. But first of all, if it's right, it's very exciting.
Yep.
Someone wins a Nobel Prize. Um, and it's good to remember that we do ultimately care about connecting to the real world.
Sure, we do.
Um, it's a fact that the Planck scale is very high and gravity behaves very, very, very close to classically in almost every scenario we can measure in the world, in the real world. So it's hard to find examples where quantum gravity should even matter for predictions.
Mm-hmm.
And so I think that something like this is very exciting and is worth being excited about.
Um, is John Schwartz still active in research?
He put out a paper related to this actually. He put out a paper thinking about realizations of the dark dimension scenario in E8 times
Oh,
E8 heterotic string theory, where you use the M theory interval as the
right.
fifth dimension. So he's definitely, he shows up to the department. He participates from time to time. Certainly
I
not,
see.
he's not there every day, but he certainly
Yeah, he's
participates.
retired, right?
Uh,
Is he?
I actually don't know if he's officially retired. He shows up to the
Okay.
department, so.
Okay, I see. So we were talking about distance conjecture. So
Huh?
one thing that I wanted to talk about, distance conjecture says that there's a tower of light states, right?
Mhm.
In the corners. But
Mhm.
how does that tower become light? That's up for like grabs. But there was this thing called emergent string conjecture
That's
that
right.
kind of establishes that, not establishes, but like conjectures that, okay, it has to be either one of the
Yes.
two things. So what
Yes.
is emergent string conjecture?
So the emergent string conjecture, um, closely related to the idea that we should call this duality conjecture,
Hmm.
tells you that there are sort of two possibilities for what that weakly coupled tower could be. Namely, it could either be the tower of Kaluza-Klein modes from a dimension that's getting large. So
Hmm.
as the dimension gets large, then the wave modes along the extra dimension get very light, and it leads to a new weakly coupled description, namely effective field theory in the higher dimension. So
Hmm.
that's the sort of new description that's opening up. An example of this in string theory, of course, is take type 2A string theory, make the string coupling very high, and you find that the
Hmm.
M theory circle opens up.
Right.
Um, the other example is where the tower that's becoming weakly coupled and light is a perturbative tower of string excitations. So a tower of string oscillator modes becoming very light. And in this limit, you would have a perturbative string theory description. Um, the logic is sort of that. So first of all, you can have a decompactification. That's fine. And then the other logic is that the only really way you can have a weakly coupled, maybe a way to say is that there's sort of two ways you can have weakly coupled gravitational effective field theory. One is as an effective field theory, where your expansion parameter is effective field theory parameter. It's the scale, energy scale related to the cutoff. So that, fine, that's weakly coupled in the regime where you don't go to high enough energies.
I mean, cutoff is in the denominator.
The cutoff is in the denominator. I'm just
Right. I
saying
mean,
it's
you
not
said
weakly
cutoff,
coupled at
right?
the cutoff, of course.
Sure. Okay. I see.
Yeah.
I see.
Um, and the other is string theory. The other is
Sure.
perturbative string theory, which is a weakly coupled theory of gravitate that includes gravitational interactions.
Hmm.
Um, one reason to believe this is just that we don't have any other idea um, of how to make a weakly coupled theory of quantum gravity. I mean, I think a lot of people probably believe that that's the only way. Um, but it's worth saying that what, for instance, the paper that proposed the emergent string conjecture checked, like the actual content of the conjecture is the following: is that what you don't find is you don't find a limit where the lightest states are, say, a membrane.
Hmm.
And this is a non-trivial check. You check in Calabi-Yau compactifications using some sophisticated, complex differential algebraic geometry that in every limit, so certainly in some limits, membranes are getting light, but in such limits, strings are getting lighter faster.
Hmm.
And that's a non-trivial check. Um, and they find that indeed such membrane limits don't exist, at least in the class of examples they check.
I see. So I was the only place that I have read this is in one paper. So I was reading this paper by Bedroya and Steinhardt
Uh-huh.
on scale separation. So
Uh-huh.
he mentioned. So they
Was this
mentioned
the
that
paper on a scale, like an
uh,
ADS related to
I think
holography?
I think it's DJKT versus scale separation. Sorry. No, sorry, that's wrong. It's scale separation versus holography. Yes,
Yes,
what you're
yeah,
saying.
yeah,
Right,
yeah,
right. So, but by the way, I think that paper is longer than it's supposed to be. I mean, it should not be that long. But
yeah.
anyway,
Th apologize to Alec. This is a paper that Alec told me a lot about in person over the summer at the Summer Workshop.
sure.
I haven't actually read the whole paper. Um,
I actually presented that paper in my department. That's why I
Great.
know.
Yeah, yeah, yeah.
But the thing is that, so I think most of the paper is just a review how to make black brain solutions and things
Mhm,
like that.
mhm, mhm.
So one thing that I read in that paper is that emergent string conjecture has some bottom up evidence too. So do you know about that bottom up evidence?
What was their
So I think it was like if you talk about gravitational amplitudes, then the density of states scales that kind of gives you this
is it the
that
idea that
potential
like the
string
density of
theory.
states should scale in the manner of a two-dimensional conformal field theory?
I'm not exactly sure, but it was something which has to do with density of states. Uh,
Yeah. I'd have to read the paper. I mean, but the
mhm.
yeah, there's some sense in which this has actually been seen from quite a few perspectives. There's some sense in which the sort of black hole density of states eh,
Oh,
behaves in some sense as being related to two-dimensional conformal field theory. This is sort of related to the two dimensions
I
transverse to
see.
the black hole horizon, is maybe a way of thinking about
Mm-hmm.
it. This may be what they
I
were
see.
thinking about.
I can put that part of the paper in the podcast as well. But
Sure.
yeah, that was interesting to see that. Okay, the emergent string conjecture has some bottom up evidence as well. So one thing that previously I said that distance conjecture has many different versions, right?
Mhm.
So when you were talking about the supersymmetric distance conjecture, you said that this distance conjecture is in the moduli space. So
Yes.
do you think that we need a distance conjecture on the space of theories themselves
Yeah, I mean
and not on the
that's
moduli
very
space?
much what like this like ADS or DS distance conjecture related to dark dimension, because when we're talking about the cosmological
Hmm.
constant, this is moving into sort of the fields, the configuration space, the space of theories. Um,
Hmm.
yes, I mean I think if the distance conjecture is going to be some universal property of quantum gravity beyond supersymmetric moduli spaces, then it has to be a statement about the space of theories. Um,
And we need a metric over the space of
and we need
theories.
a metric on the space of theories. That's right. There's good physics in certain contexts, of course. There's good physical ways to think about metrics on the space of theories, right? If you have there's a metric on the space of theories which is related to the kinetic terms of the effective of the fields.
Sure.
There's also something like Zomolodchikov metric on the space of conformal field theories.
Right.
Um, when theories are not connected by massless or maybe light field deformations in field space,
Hmm.
it's hard to know what the right notion of distance is. A number of people have proposed notions of distance uh, related actually to the Cobordism conjecture. What you might want to say is that any two theories are connected by the Cobordism conjecture by a domain wall, and you might want to use the tension of that domain wall as some measure of the distance between the theories. Um,
Hmm.
I think there hasn't been a really like fully conclusive realization of this idea, but various people have written a number of papers on trying to make this idea work. And I think it's a good idea, and I hope people keep thinking about it.
Right. I mean, so there are for example, there was this paper by Palti, I think.
Huh?
It talked about the metric over the DGKT vacua.
Yes.
So there
Yes.
are proposals for the
Yes.
metrics on vacua, but is
Huh?
that different from metrics on the space of theories, or is that the same thing?
Well, I think in because of the Cobordism conjecture, the perspective, if you read, say, the introduction to our paper on the Cobordism conjecture, the one point is that the space of theories is the space of vacua.
Hmm.
Or maybe better, one other way of saying is that when you say space of theories, you mean space of vacua, or maybe you mean space of configurations. Because the Cobordism conjecture says that there's only one theory. So I can tell you the space of theories. Single point.
Hmm.
That's the space of theories. But that's not what you mean, right? You mean the space of low energy effective theories, of limits, of different asymptotic conditions you can put. Things where, say, type 2A and type 2B are two different theories, as opposed to two different vacua of one theory, for instance. Um,
I see.
so yes, I would say that when I talk about metric on space of vacua or metric on space of configurations, that's also, I think, you could call metric on the space of theories. Um,
I see. I mean, there was this paper recently. It was by Alexander Maloney and some other people. I think Alexander Bellin. I think he was
uh-huh,
one of the authors. It was about a measure on the space of CFTs. So they were talking
uh-huh,
about
uh-huh.
like measure on the space of CFTs, which goes beyond two 2D CFTs. I think. So I don't know if that was something that can be used to find a measure, but I'm not sure. I'm just saying that.
That'd be very interesting. I mean, there's I think measure on space of theories is probably easier to define
Mhm.
than metric, um,
Right.
because there's sort of a natural physical guess for what the measure on the space of theories is. It's like the related to things like the amount of degrees of freedom the theory has, things like that.
Sure.
Like counting theories measured based on how many degrees of freedom they have. Um,
Right. Right. Right.
to go from that to metric is a little bit more complicated, but there's also quantum information things you can think about. You can think about like how complex is the process of turning one system into another system and try to use that as a
Yes.
notion of distance between systems.
I mean, there is this called the Fisher metric
Yeah,
on
yeah,
statistical
for
manifolds,
instance.
right?
Yeah.
I mean, we do know that there are manifolds on which you can put more than one consistent matrix, right? So,
Yeah, I mean, in fact, I'd say every manifold.
sure, yeah, I agree. So, what about if there is no, unique metric for the space of theories? Then what do we do?
Yeah, I think if there isn't a first principle, well-motivated notion of a metric on the space of theories, and yet the distance conjecture is still correct, meaning there's something it means, then there's
Hmm.
probably some structure on the space of theories that is really what the distance conjecture is telling us about. Um,
I see.
I think what I might hope for is something like the sort of finiteness principle that the distance conjecture is telling you that maybe here's another point to make. There's this notion of emergence in the Swampland
Hmm.
proposal. This is emergence proposal, where you view the metric on, say, the moduli space as arising from integrating out heavy fields. Um, we have examples of this where it's totally clear. For instance, at a conifold point, you integrate out the BPS D3 brane that's becoming light, and that generates the singularity in the metric, whereas without that, you wouldn't have had a singularity in the metric. So there's a picture
Sure.
where the moduli space starts out in the UV as like compact.
Hmm.
And the reason why you get infinite distance points is because states became light there. And
Oh,
because the states became light, when you integrate out the states that are heavier than the cutoff but part of this tower, you might think of actually this is maybe not quite the right way to say, but in any case, you might view that infinite distance as related to integrating out some states. They may not be the states in the tower becoming light, but there's some duality, there's some relationship.
I
Um,
see.
and so there might be some sense of sort of finite volume of the space of theories with
Hmm.
fixed cutoff. I think that is a very natural thing to expect. And again, it's also related to this cobordism conjecture because if you have a black hole,
Hmm.
by the cobordism conjecture, the sort of interior of the black hole can fluctuate to every other theory.
Hmm.
You want those fluctuations not to contribute an infinite amount of entropy. In fact, you want them to contribute no more than the black hole entropy. And so, there needs to be some mechanism by which the fluctuations of the interior of the black hole over the space of theories does not overcount the black hole entropy. And so this is some reason to think that the space of theories might have some finiteness property.
So I have two to three more questions before
Yeah.
we can wrap this up. So one thing, so um, I mean, I can kind of try to guess that what your opinion would be on this thing because you are a student of Qumran.
Huh?
So do you think that the ADS no scale separation conjecture is correct?
I I I I mean personally I really don't know. I find the work required to check it to
Hmm.
be very hard. Uh,
Okay,
for instance, checking validity of something like KKLT is very hard. Ruling it in
great.
or ruling it out is very, very hard. And it's a sort of physics and calculation which I don't think is my strong suit. I think My strong suit is, more topological things, more qualitative structural things.
Hmm.
Um, and so I genuinely don't feel like I'm qualified to
Okay.
say one way or the other. I think that the reasoning behind it is very reasonable, is very good, very in line with other things we believe are true in the swampland.
Hmm.
Um, I think it's very hard to imagine how a scale-separated vacua could be holographic in string theory, just because the mechanism of holography in string theory is, you put a stack of branes and they back react and create the
Yeah.
geometry. And it's
Yeah.
hard to imagine how you could put a stack of branes whose back reaction is to sort of close the angular direction so strongly that it becomes very small.
Hmm.
It's hard to see how that can happen. But of course, that's not a proof or anything. I mean, I think there's a lot of people doing really, really good work trying to check these KKLT vacua. I saw you had Manky Kim on recently, for instance. Manky Kim has been doing incredible work trying to
Yeah.
use things like string field theory to calculate the corrections that need to be taken into account to check if these proposed KKLT vacua
Hmm.
are really solutions to the equations.
I mean, for
Um,
example, this paper by Bedroya and Steinhardt that I mentioned, in that paper they kind of showed that they have an assumption there, but they kind of showed that you can't have DGKT, in holography because you don't have the decoupling limit.
Yeah, I mean, yes, and I think that their paper is trying to formalize sort of what I was saying, which I mean, I think is a common perspective is that
Hmm.
there's something weird about scale separation and holography. There's something weird from the perspective of the mechanism, the underlying physical mechanism for holography in string theory. It's hard to understand how that could happen.
Hmm.
Um, but of course, that's not an argument. I mean, it's not a proof. It's an argument,
Yes.
maybe even a good argument.
Hmm.
But ultimately, for this sort of thing, that's something I'm excited about dark dimension because dark dimension we don't have to argue. We can wait for the experiment and we can see.
Sure.
Uh, and that's again why I think this is really more science than math, more hypothesis than conjecture. The proof is in what's true of the real world. Um, and I think there's a lot of, I mean, what I think a lot of people would point out, and I think is a very fair thing to point out, is that we live in a universe that seems to have a positive vacuum energy.
Yes. Sure.
And of course, the most natural explanation of that is that string theory has long-lived metastable de Sitter vacua. That's a completely reasonable thing to think given the observations of the universe.
Yeah.
And so we're in this predicament where I think both sides are reasonable. And
Yeah.
and I think there's different approaches. One is to say, that's an interesting hard problem. I'm going to work on something else, which is what I do. There's to say, it's an interesting hard problem. I'm going to work really hard on it, which is what folks have been doing, and I think it's really good. One way or another, this De Sitter swampland conjecture has led to tremendous improvement in our ability to construct and check candidate KKLT vacua due to work of, say,
Hmm.
the folks at Cornell, the sort of expanded Cornell group that I think sometimes doesn't like being called the Cornell group, but anyway, the Cornell group.
I mean, what else do
Um,
you call it?
sorry?
It is Cornell. What else do you call it? It's called Cornell
Well,
Group.
they've graduated or finished their postdocs and moved on to
Okay.
many different places, but
Sure.
still the Cornell group. Um,
Well,
it's funny.
I
Naomi
mean,
Gendler.
McLister is still there.
Sorry?
McLister is still in Cornell, so he was like
Yeah, 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 yeah.
the seed. Okay. Yeah,
Yes.
you were saying something.
I was saying, and Naomi Gendler made a very funny comment to me once when I called her a swampland person. She said, "No, I'm a landscape person," which, sure, fair
Sure.
enough.
Sure. Fair. Yeah.
Um, two sides of the same coin. Um,
Is it?
I think that it's great that we're being more careful. It's great that we're trying to figure it out.
Mhm.
Because it is an interesting and important problem, right? It is an
Yeah.
interesting, like understanding our universe is interesting. Trying to understand quantum gravity in a positive cosmological constant universe is hard. It's hard to even. This is related also to what we are talking about closed universes, right? Our
Mhm.
cosmology, if it's de Sitter,
Mhm.
the finite time slices of de Sitter are closed.
Right.
So if we
True.
think about the quantum mechanics of de Sitter, we're forced to take into account the observer.
I mean, I once thought that the crackpots that deny that gravity exists, those people are inconsistent with gravity, and those people are in the swamp. So they are
Yeah, I mean,
swampland people.
I've never understood, for instance, attempts to try to treat gravity classically. I know that like Jonathan Oppenheim, for instance, is
Yeah.
I mean a very serious person and has a
Yes,
very
sure.
serious perspective on gravity treated
Mhm.
classically. Um, I do also think, I don't know, Occam's razor, the simplest possibility is that gravity, like everything else, is quantum mechanical.
Yeah,
Uh,
when I was in ICTP in 2019,
yeah.
so do you know about Kyriakos Papadopoulos?
Uh, yes, a bit.
So, so he used to be at ICDP at that time, and he gave. So I've never heard that argument before. He gave me, and it was so simple, and I was like, how did I not know this? So he told me that if gravity is not quantum mechanical, then you can break Heisenberg uncertainty principle using gravitational waves because you can just increase the amplitude without increasing the frequency, and you can.
Mm, mm,
Uh,
mm.
so
Well,
that was the argument.
I'm not sure I understand the argument because, I mean, the
Mhm.
Heisenberg's uncertainty principle is true for classical waves.
True, true, but
What's
the
weird is that it's
problem.
true for particles too. Like that's the, yeah. But
Well, I mean, the problem was that the thing that he was saying is that you can detect the position and sorry, the position and the momentum of a particle to arbitrary precision using
oh, using
gravitational
like,
waves. Yes,
I'd have to see the argument because my first
sure.
instinct is to say that that wouldn't be true because if you try to focus the waves,
Yes,
like for the same reason as the Heisenberg uncertainty principle is true
yeah.
for waves, just if you try to focus the waves, you increase their spread in momentum.
Well, so as far as I understood, what he was saying is that if you try to, measure the position of a particle to a very
Mhm,
high precision, you will have to use a gravitational wave of a very small frequency, right? Sorry,
mhm.
a large
Very
frequency,
high
or
frequency, yeah, yeah.
yeah, or small wavelength.
Yes.
But the thing is, the normal argument that goes is that if you have a very small wavelength, then you would disturb those particles by a large amount,
Mhm.
and therefore you can't find the momentum. But the thing is that you can so in for classical waves, the momentum transfer is also proportional to some power of the amplitude. So you can just decrease the amplitude arbitrarily.
I see. You're saying that the amplitude wouldn't be quantized.
Yes, that's what he was saying. So therefore, it has to be the gravity has to be quantum mechanical.
I'd have to think about it more because I mean,
Sure.
for instance, what like Jonathan Oppenheim has studied, right? I mean,
Hmm.
and in many other contexts, I mean, it's perfectly consistent to drive a quantum system by a classical system.
It's consistent, sure, but this argument kind of made me think that okay,
Mm.
probably you can, violate Heisenberg's uncertainty principle. I mean, one argument against it that I can
Mhm.
see is that you may decrease the amplitude to such a small amount that you will not be able to detect it at all. That's the only thing that I can see which can be a
Oh,
wrong argument.
sure, sure. Yeah,
Yeah,
that's a fair
that's the
point.
only thing that I can see.
Your detector, of
Otherwise,
course, being made out of quantum mechanical degrees of freedom as
right,
well.
right,
Yeah.
right. I agree. So yeah, that was the only thing that I could think of. Otherwise, this argument is pretty not. It's not bad, at least,
Mm.
to see that gravity has to be quantum mechanical.
I
Okay,
mean,
so yeah,
maybe
sorry.
just one comment on that question. Like,
Sure.
why do I think gravity needs to be quantum mechanical?
Yeah.
Uh, I mean, I it from a, it dep depending on your interpretation of quantum mechanics, it might
Hmm.
not make sense for gravity to be class not for the universe to not fundamental if some of the universe is quantum mechanics, not for the whole universe. And the reason is that if your interpretation of quantum mechanics is that a superposition describes your lack of knowledge about the universe, say in something like quantum Bayesianism or what I would call Copenhagen. Um, if saying that say the Earth is in a superposition of here and here just
Hmm.
means that you don't know whether the Earth is here or here,
Hmm.
then I don't see how that could do anything but produce a superposition of the gravitational field of the Earth here and the gravitational field of the Earth here.
Yeah.
Because if you look and you find that, oh, the Earth is here, then you'll be very surprised if there isn't also the gravitational. You'll be more than surprised. You'll violate the gravitational Gauss law,
Yes.
the gravitational constraints. I mean,
Right.
if quantum mechanics is simply a description of our lack of knowledge about the universe until we look at it, then I don't see how the whole universe can't be fundamentally quantum mechanical if part of it
Yeah.
is.
I mean,
Um,
there is this experiment. Okay, I hope that I'm able to reproduce the
mhm,
argument correctly. But there was this experiment called the Page-Kalkar experiment. So the
uh-huh,
Page-Kalkar experiment says that suppose that you have two gravitating bodies and you have a probe particle, then you
mhm,
can ask the question that okay, if you sorry, you have one gravitational body.
mhm,
So if you put this gravitational body in a superposition of being here and here, then the question is the expectation value of the probe particle in between these two places, or is it close to one of these two
mhm.
positions? And when the experiment is done, it's close to one of these two, it's not in the middle, right?
You mean the like variance, not the expectation.
Yeah, sorry, not expectation, of course. Yeah,
Expectation, I assume, is always.
measurement. Yeah,
Yeah,
expectation should be in the middle, of course.
yeah,
Yeah. So,
indeed.
David Wallace is a philosopher who also has a physics PhD, and he supports Manifold interpretation. And he said that if Manifold interpretation is correct, then you have kind of shown that gravity has to be quantum mechanical. But I don't understand why that is required for it to be shown. But yeah, that experiment was interesting in you know answering this question. But I don't think that this question has been answered because there are people like Jonathan Oppenheim who think
Mhm.
that it's not going to happen. But I will be surprised that if gravity is not quantum
I
mechanical.
mean, another piece of evidence as to why gravity is quantum mechanical
Hmm.
is just that it is in string theory. So if your reason why you think it shouldn't be quantum mechanical is you think it's inconsistent to treat it quantum mechanically, that's just false. Like string
Yes,
theory, whatever else string theory is, it is a internally consistent theory of quantum mechanical gravity.
right,
And in
right, right.
string theory, if you put a mass in a superposition, you create a superposition of the gravitational field.
Hmm.
It treats the graviton quantum mechanically like everything else.
I don't know if people like Jonathan Oppenheim say that it's inconsistent to be quantum mechanical, but yes, of course it's not inconsistent because we do have
I don't
one
think
one.
he says that. Yes.
Hmm.
And my
Yeah,
point is just combining quantum mechanics with gravity, we know is not impossible. We just know it's hard.
of course it's not. Yeah, I mean, but as you can imagine, a lot of people will be very pissed off by you saying that because it's in string theory, so it has to be quantum mechanical.
Yeah, I mean, yeah, maybe this is a fun topic to comment on. I mean,
Sure.
there's a question about whether string theory is actually the only game in town in the technical sense of is it the only consistent theory of quantum gravity?
Hmm.
And if our cobordism conjecture is true, then it is
That's what I was gonna say.
for sort of a tautological reason because we say that there is only one theory of quantum gravity.
Hmm.
So if anything else is a consistent theory, then it is actually dynamically part of string theory.
Hmm.
Uh, Now you could argue that maybe there's lots of parts of the landscape that look nothing like what we typically think of as string theory, so maybe you shouldn't call it all string theory, you should just call it quantum gravity. But if
Yeah,
it
but semantics.
semantics, yes,
Yeah,
semantics. Yeah.
sure.
Um,
I mean, about string universality? That's a program that people
Absolutely.
have. So I think if that program, I don't know if that will be achieved, but if that is achieved, then you can say that string theory is the only game in town. Then why not?
Correct. I mean, the only way out is to say that the underlying swampland principles are wrong. For instance, yeah, I mean, for instance, maybe I can say the following. There are certainly things that you might call quantum gravity theories that are not string theory. An
Hmm.
example is JT gravity.
Yes.
Not a member of the ensemble described by JT gravity, but JT gravity just as quantized directly
Hmm.
is not holographic in the standard sense and
Hmm.
has information loss. In pure JT gravity, if you have information fall into a black hole, it doesn't come back out. It goes into baby universes and the page curve goes up forever. Technically, what I'm talking about is the entropy of the ensemble average state, which whose does not satisfy the page curve, which goes up forever.
Right.
If you say I'm using it as an ensemble and I mean really I'm trying to get at the members of the ensemble, then sure, those are presumably part of the string landscape.
Hmm.
But I think the important criteria is whether or not black holes have unitary evaporation, or not the black hole information paradox is resolved.
Hmm.
And so if you give up on the idea that black holes have unitary evaporation, if you give up on the holographic principle, then sure, maybe there are other things you could talk about.
I see. I see. That makes sense. I
Yeah.
mean, okay, so it may be it may be a question that is out of line, but why do people? Okay, I do see some reasons to study it, but why do people spend so many resources to study JT gravity? I
I
mean,
mean, I
when
think
it
there's
has,
a number of answers to that. I think one of the biggest reasons is just that we can.
yeah.
Um,
I
me,
mean, I know
me,
that it's dual to a matrix model. Sure, that's good, but apart
what I
from
mean
that,
more is just that it's an example of a gravitational path integral that is tractable enough that we can actually really calculate things.
okay.
Now, of course, the question of interpretation is a different one. Like, is how analogous are we supposed to think of it as between like how analogous are we supposed to think of it to string theory?
Hmm.
Um, and that I mean that's a whole other discussion. But I mean people do what is possible. Uh,
Sure.
and we've learned and genuinely we've learned quite a lot. I mean, I think we've learned all of the things we've learned about replica wormholes, for instance, are very
Hmm.
exciting and I think still need to be understood. You know, I mean, maybe one way to say it is like, do I think that replica wormholes are how information gets out of a black hole in string theory? No, certainly not.
Hmm.
Because I think that string theory is not an ensemble average. I think that string theory is a single theory.
Hmm.
But then you have to answer, why do replica wormholes get so close to the right answer? For instance, right? And I
Yeah.
mean, a more basic example of this is semi-classical gravity does not have black hole microstates. Yet semi-classical gravity, you can calculate the Euclidean Schwarzschild black hole, and you find that the entropy it tells you should be is the right answer.
Well, you know about entropic gravity of Eric Verlinde?
What is it?
Eric Verlinde has this thing called entropic gravity. So
Oh, yes, 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 yes.
so he can derive Einstein field equations from it, but it's not the correct thing, right?
Well, I guess what I'm saying is that, like, I don't think it's a coincidence that the
Okay.
semi-classical gravitational path integral seems to give the right answer for certain quantities.
Okay. But what I'm trying to say is that we have historical evidence for the fact that you can get correct equations from theories which are not correct.
Well, I mean, what does correct mean? I mean, no
Okay.
one is saying that we live in JT gravity, right?
Sure. Okay.
The question is it a good toy model? Like, does it accurately describe our universe? And I think that there are very obvious ways in which it doesn't, which is that maybe one comment to make is I don't know what it means to to quote unquote actually live in an ensemble. If you
Yes.
actually live in an ensemble, then with probability one, you live in a member of the ensemble. So just go to that member. Like from my perspective, an ensemble is a calculation trick. Maybe
Mm-hmm.
it's a good calculation trick, right? It's a useful calculation trick, but at the end of the day, you live in some actual quantum theory,
Mm-hmm.
unitary quantum theory, with a maybe I say an algebra of observables that does not have a center as a factor.
Yes.
Um, so I think that JT gravity has its pros and its cons,
Mm-hmm.
but I do think it's worth remembering that we actually care about a particular UV complete quantum gravity and not the ensemble. Um,
Okay. Fair. Fair. Okay. So I have three more questions. Then I have
mhm.
some two or three people's questions, and then we can wrap
Sure.
this up. So
Yeah,
one
yeah.
question that I have is that Uh, I mean, you did, mention that, so let's expand on that. So, what are baby universes?
So historically, the idea is that we live in some, you know, big universe, and small patches of the universe could potentially disconnect as a closed bubble, closed universe, and then reconnect at some other point in space-time. And so the idea is that our universe is a parent universe, and that's a baby universe, the sort of offspring of the parent universe. Um, but the study of baby universes is really more the study of closed universes. Baby has this connotation of small, And if our universe is closed from the technical perspective, it would qualify as a baby universe in this context of discussions of the baby universe Hilbert space. But I think the name is evocative, and it's a I don't know, I don't find a problem using the name. Um, so baby universes the idea is trying to understand the quantum mechanics of closed universes, of universes that are not connected to asymptotics, not connected to an observer, just floating sort of in the void. Um, and
Mhm.
a statement which is equivalent to the Cobordism conjecture, at least from my perspective, is the statement that the closed universe quantum mechanics is trivial, that there's a unique state, there's no interesting dynamics, and essentially another way of saying it is that the conjecture would be that in quantum gravity, to emit a baby universe or not to emit a baby universe are physically equivalent, are gauge equivalent.
So to emit or not to emit means same
Yeah,
thing, right?
exactly. Um, in other words, it does. There's a basic physical reason for it, which is
Mm-hmm.
that if you're not in the baby universe, what does it even mean to say it exists? This, of
I
course,
see.
touches back on things like measurement problem and meaning of
Right, right, right.
observer. But I should say that I think that technically we've learned something quite interesting, which is that this is true that the baby universes are have a trivial quantum mechanics if and only if black holes evaporate unitarily.
And you think that this is in line with Cobordism conjecture, right?
Yes, yes. Yeah.
So I was going to ask this
I think
earlier.
it's actually essentially equivalent. The
Right, right,
reason,
right.
yeah, the reason is that the quantum states of closed universes are these sort of closed manifolds we're talking about.
Yeah,
Saying there's only one is saying that they're all dynamically connected. So
I
that's
see.
how the two statements are closely related.
I was going to ask this earlier, but let me ask this now because I think it's more relevant now. So is Cobordism conjecture in this scenario, is it the same as Wheeler-DeWitt equation?
No. So the Wheeler, right. So the Wheeler-DeWitt equation, of course, says that the time evolution in the bulk of quantum gravity or in a closed universe is a gauge constraint. In the sense,
Okay,
as we discussed before, of it's a redundancy of the description.
sure.
Um,
So when you say, wait, so when you say trivial dynamics, does it not say that Hamiltonian is zero?
Excellent. So Hamiltonian is zero is the first step. I'm
Hmm.
saying that the Hilbert space is one dimensional. The Hilbert space is C, it's just the
Oh,
complex
okay.
numbers.
I see. I see.
But of course, it's related. You can kind of think of it, the Wheeler-DeWitt equation says that the net energy in a closed universe is zero.
Yes.
This one dimensionality of the closed universe Hilbert space says that the net entropy in the closed universe is zero.
Oh, so
Because the
so it says
entropy is
that,
like the log of the dimension, is roughly related to the log of
right.
the dimension.
So what you're saying is that it's Wheeler-DeWitt equation plus more.
It's stronger than the Wheeler-DeWitt equation. And the
Yes.
reason is that in models like JT gravity,
Hmm.
the Hilbert space of closed universes is not one dimensional,
Hmm.
but it still has some version of Wheeler-DeWitt equation that should still hold.
I see. I see. So what you're saying is that the energy of the universe is zero and then the
That the
entropy is
energy of
zero.
closed universes being zero is the Wheeler-DeWitt equation, H equals
Yes.
zero.
Sure.
This condition is that the dimension of the closed universe Hilbert space is one dimensional.
Which means
The
that the
star.
entropy is zero.
It says that entropy is zero, exactly.
So,
But
but
zero
if,
as a gauge constraint, not just happens to be
oh,
zero.
right, 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 right. Okay.
Zero in every state.
In every state, I see. So, is it related to this thing that there is only one possible universe? That's also
100% it's related to that. Yes,
okay.
it's some very strong form of the statement that physics is ultimately relational or subjective. I mean,
Hmm.
this is the Hilbert space of describing quantum mechanics of universes that you are not in.
Hmm.
It's universes that you are not inside of. They're
Oh,
out there somewhere in the void. And the statement precisely is that there is nothing physical you can measure about such universes, which I think phrased that way is a very reasonable statement.
hmm.
If you then think about it in terms of statements about the configurations of the closed universes, sort of semi-classically, it looks very ridiculous. It's saying that all of those states are just proportional vectors in Hilbert space. They're, if you normalize them, their overlap, the transition amplitude between any two is one.
So, I'm pretty sure you know about the Witten's bubble of nothing, right?
Mhm.
So how is this universe different from nothing?
Yeah, so the bubble of nothing is saying in our universe we could have a patch of the universe that sort of has vacuum decay to nothing, where a hole opens up where there's nothing inside.
Mm-hmm.
Baby universe is in some maybe in some sense a complementary process where instead we have a patch of the universe and it instead pinches off and goes off on its own. In the bubble of nothing, there's no interior anymore. It's not going somewhere. It just is gone.
Right, but what I'm saying is that if you have this thing where you're saying that that the dynamics are trivial and
Ah,
there's only one possible universe, how is that different from nothing? So you still have a space time,
yeah, I mean
but you don't have a
they're
space.
conceptually related. Um, they could also be related to certain perspectives on black holes. So I think what we've really learned, especially from the sort of replica wormhole stuff, um, is that if information in black holes is lost, we know where it goes. It goes into
Mm-hmm.
the baby universe, sort of the entire interior of the black hole pinches off as a baby universe, and if the information does not come out, that's where it went. Now, the condition that the net entropy in the closed universe be zero forces the information to come back out. Because if the information is trying to fall into the closed universe, but the closed universe has no capacity for storing information, then it comes back out.
I see.
The connection to bubble of nothing would be that there are other perspectives on black holes where you imagine that space-time ends at the black hole horizon and you have sort of degrees of freedom, maybe holographic degrees of freedom living on the horizon that realize the black hole interior. And this sort of perspective comes under many different names. Um, one would be in the context of the fuzzball program.
Mm-hmm.
One would be to view this just sort of as like the basic statement of the holographic principle that you can replace the black hole interior by instead thinking about there being degrees of freedom living on the plane and then nothing inside. Sorry, on the horizon and then nothing inside. So these ideas all are kind of connected. In fact, I've really wanted to make that perspective more precise, like saying that the end of the world branes predicted by the Cobordism conjecture are in some sense related to holographic screens. I would really like something like that to be true.
Mm-hmm.
Um, this, of course, is a much more detailed quantitative statement as compared to the qualitative kinematic statement of the Cobordism conjecture.
Right, right, right. So I have like two more questions. So one question is that do you have any advice for younger students about how to make collaborations or build collaborations in PhD?
How to build collaboration? That's a great question. I would say for myself, first of all, I got very lucky. I was lucky and privileged enough to get to take a class from Cumrun as an undergrad. Um, so I got to know him in a context where, he was my teacher and I asked him, do you have projects for me to work on over the summer? And it sort of grew very naturally. Um, it's funny actually. And then my collaborations with this large group of authors with Tom Rudelius, Ben Heidenreich, Matt Reese, Irene Valenzuela, and Miguel Montero,
Mm-hmm.
counting because there's six authors and we've written a couple papers together. That was a collaboration that we started in grad school. We started um, just before the pandemic, and then working on those projects carried us through the pandemic, which was wonderful because it was nice to have that sort of interaction uh, throughout the pandemic. Um, I think that it can be difficult, especially as a younger student, as a, getting sort of your footing in the community. I find that most of my projects come from conversations at conferences or just conversations in around the department, where we talk about some idea and then it seems like there's something to think about, and we agree to meet and continue discussing. Um, I would say, one thing to rely on is if your advisor is willing. I think having your advisor introduce you to people is a really good idea.
Mm-hmm.
Of course, again, in my case, I was lucky enough to have a very famous and well-known advisor who has the degree of connections to be able to introduce me to people.
Mm-hmm.
Um, but I think another thing to say, a special piece of advice for younger people, is that something to know is that most research projects or most like starts of research projects don't necessarily go anywhere. Um,
Yeah.
this was really hard for me. at the beginning of grad school, I had a paper I had written with Cumrun when I was in undergrad, but then we didn't put out the Cobordism paper until my third year, and there were a lot of sort of little starts of projects in those first 3 years that didn't go anywhere. And I found it very frustrating. I felt like, am I doing something wrong here?
Hmm.
And the answer is no, is that research is hard and research projects fail, and it's good that they fail. If a research project isn't working, then the right thing to do is to put it down. You shouldn't keep trying to make something work that isn't working. Of course, if you think it could work, you should keep working at it. But if it isn't going
Hmm.
to work, then it's okay to say this isn't working. And so what I would say is, don't get discouraged to younger people. Don't get discouraged if you have some interaction that you hoped would lead to a project that maybe doesn't. And I would say keep trying because once you sort of establish yourself and you have a sufficient number of projects and sort of ideas floating around in your head, it becomes just easier and things will start sticking. There's sort of
Right.
Actually, I had this experience, and many other of Cumrun's students had the same experience, where there's really a phase transition, maybe around third year of grad school for us or whatever, and this of course depends on advisor style as well. Um, but it's sort of a phase transition where, at first you're feeling like I'm just desperate for projects, I can't find enough projects, and then way too quickly you have too many projects to handle.
Yeah.
And this is a natural progression. So, you know, it kind of grows exponentially, and there's a reason why, right? Like you think you have one conversation, then you have another conversation, and those people have conversations, or at least faster than linearly, The
Hmm.
the number of interactions and conversations you have will start growing the more you start getting out into the community and interacting. I
So
would say
would
it's
you
good to
also
go to conferences.
Right. Would you also say that if you started as you said that most projects don't go anywhere? So would you also say that if you started a project with some collaborators and it doesn't go anywhere, then some younger students start to think that these collaborators, especially if they are senior than them,
Yes,
then these collaborators will think less of me because the project didn't go anywhere. So, but you're saying is that it's normal.
I would say it's normal. I mean, myself, I had a project in my last postdoc that we worked on for like a year and a half, and it ended up not really working out. And it's hard. I mean, it's frustrating, and it's hard to not feel like you've failed. Um,
Mm.
but that's research, So
Right.
so I would say try to not get discouraged. Of course, it's not possible to not get discouraged entirely, but it is part of the research process.
So
The natural part
if
of the
you
research process.
Sure. So if you're in a big place, then
Yeah.
you will find a lot of people to talk to. But if you're in a small place where you don't have enough people to talk to, then you have to go to conferences, or do you have to like send emails to people to collaborate? What do you do?
I would say, yeah, I mean, I would say first of all that I have a privileged perspective having gone to a big place and
Hmm.
worked with a famous advisor and sort of had the benefit of that. I do think it's very important to go to conferences. If there's a subject you're interested in, I think a lot of projects start at conferences, and to talk to people when you're there. Um,
Hmm.
I would say try to avoid bugging people. Like if someone, don't interrupt someone's conversation, but it's totally normal to say to someone, oh, I read your paper, I have this thought about it. I would say if you're emailing people, sort of cold emailing people, the one thing I
Hmm.
would I would advise is to have something like have a question or have a thought or have
Yeah.
read their paper and have some sending an email to someone and saying, "Hey, can you research with me?" It's
Sure.
it's 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 just it's not clear what the person is supposed to do with that. Whereas if
Yeah.
you say, "Here is something I read in your paper, I found this interesting, I have this question, I have this thought," then you can
Hmm.
start a conversation. I think that's a better
Sure.
way to go about it.
Right. 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 Um, one more thing that I wanted to say is
Mhm.
that do you think that so of course consistency is good, but do you think that when it comes to research, consistency is important, but do you think that perseverance is more important than consistency? That you
Um,
keep going even if you fail at some projects.
I think that's very important. I think that
Mm.
that amount of perseverance is very important. Is if projects aren't working, not to take that as a sign. And of course, this is something that I'm guilty of myself, but
Hmm.
not to take it as a sign that you can't do research or something like that. It's important to have that sort of perseverance. Um, and I guess also I would say that, it's also important to work on things you find interesting. And if you find something interesting,
Hmm.
then you'll keep thinking about it because you find it interesting. And I think that that's also very important.
I mean, w- do you think that so I do think that you should work on things that you find interesting, but what about what you want to work on and what you find interesting is not a hot topic right now?
Yeah, that's a tricky question. And I mean, I'm a postdoc. I don't have a faculty job yet. I'm not tenured somewhere. I'm still
Hmm.
navigating this myself.
Hmm.
Um, I think that it is important to be aware of the hot topics and know what's going on. But I also think that it's important to have your own sort of defined research interests. Um, so if you find a hot topic interesting, you should certainly work on it. And if you don't, then you probably shouldn't. Um, I don't know. I mean, I personally, maybe I can just say what I personally have done.
Hmm.
I have always worked on things that I find interesting, um, and not paid too close attention to whether it was connected to a hot topic or not.
Hmm.
Um, for instance, when I started working with Qumran, we put out this Cobordism conjecture paper. Uh, it took some time after that for me to even realize that Swampland was part of string pheno. I did not go in starting wanting to think about string pheno. It just was funny how that happened. Um, but I would say I think that it's physics is also about networking. It is also a
Hmm.
job and a community, and it's not a pure. It's also not a pure meritocracy. It's not enough for you to just do good work if people don't know about the work you're doing, um, or the ideas you have, or the way you think, and that will only come from interacting with people, going to conferences, giving talks at various places. These things do matter, um, fortunately or
I see.
unfortunately. Yeah.
Yeah, true. I mean, any advice on how to network apart from going to conferences?
Um, Again, I think that I've had a very a sort of privileged route through this, having had
Hmm.
an advisor who is well known and willing to introduce me to people and things like that. Um, I think one thing to say is just that it is important to be nice to people,
Sure.
and sort of the usual rules of social interactions apply here too. Be nice to
Right.
people. Give them, don't interrupt them. Don't, maybe we can cut some of this out, but don't, try to figure out how to say it.
Sure, it's
I
fine.
don't know if I have a good answer.
Okay, it's fine. No problem. Okay, so I have some questions. Sorry, I have
Uh-huh.
some questions from the people. So let me ask those
Sure.
questions before we wrap this up.
Yeah.
So one question is that have you ever wait? Yeah, it says that have you ever experienced imposter syndrome and how did you how do you deal with it?
Yeah, that's an interesting question. I don't know that I've felt specifically imposter syndrome in the feeling of I don't belong here. Um,
Hmm.
as I said, I've had a privileged position. I was an undergrad at Harvard, and I, felt like I fit in. Um, what I have had enormously is feeling of like frustration of, do other people think that, right? There's imposter syndrome of like
Yes.
feeling like yourself aren't measuring up, and then there's the frustration of feeling like, being externally validated. And so I
Hmm.
certainly feel that all the time, and I think it's something I struggle with, and it's a hard part of this field is that because it is such a social field, because we're not just, you know, we're doing physics because we want to understand things and we want other people to understand things, and it's a communal activity. Um,
Hmm.
it's easy to put a lot of self-worth on the sort of external validation you get from how do other people respond to your ideas and the things that you've done. Um,
What you're saying is that you still feel that?
yeah, yeah, for sure. Definitely.
Okay. I mean,
Yeah.
don't you think that if you, so I don't know if it works the same for everyone, but if you get like feedback from community in
Huh?
in the form of like getting postdocs and getting
Huh? Huh?
citations, doesn't that help to, fight this thing?
That's an interesting question. It does, in that it is something you can point to as
Hmm.
evidence of, feeling validated, feeling successful. Um, I think there's also a degree of personality. I think that there are some people who respond in different ways to external validation versus internal validation, and it's
Hmm.
something I struggle with. I'm sure it's something lots of people in our field struggle with.
Yeah.
Um, Maybe what I can say is that I don't think that it is a signal of inadequacy as a physicist. And I think that
Right.
people should know that it's not.
I mean, so sometimes I wonder if it ever goes away. For example, I'm not gonna, name the physicist, but there was a tenured physicist, a tenured professor who works on theoretical physics. He's in our field, and I was talking to him, and he said that I don't think that I have done enough in my. I was like, okay, you are a tenured professor, and you still think that.
I,
So does it
I
ever go
have
away?
some tenured professors who I know very well who have expressed similar feelings. I think there's a big degree of personality. I think that
Hmm.
there are some people who feel this way a lot and some people who feel this way not a lot. Personally, I don't expect it to ever completely go away. I think
Hmm.
that, we're driven by wanting to be successful, and I think that ultimately I'm not sure that that instinct ever goes away, but
Yeah.
I think that as you get more maturity in the field and you get more interaction with people, it it's less impactful in that you become many more concrete things you can point to reassure yourself, you
Sh-
know?
But I'm
Um,
talking about like people who are more mature than us. Like they are tenured professor, and they still think that.
and I fully expect to always feel some degree of this, I would say.
I mean,
And
I don't know if the reason to think this is the same, but for the people that I'm talking about, most of the time, their reason is that there is a person who was in their batch or in the same generation that they were, and that person is more successful than they are. So they think that okay, I should have done better so that I could be, as good as
yep.
this person. So do you think that that happens mostly, or is it, are the reasons different for different people to think this?
Um, I don't know. I mean, I think that that's definitely a very common feeling. There may be
Okay.
other related feelings, but I definitely think that's a very common feeling, and I think that that's not a feeling. I would be very surprised if there's anyone, no matter how senior, who has never felt any degree of that. Um,
Okay.
yeah.
I see. Okay.
Unfortunately,
Hmm.
this physics and academia is both a passion and a job,
Hmm.
and when those two things combine, there's tensions, right? There's a tension between the feeling that your self-worth is built up of your is it founded in your career, and the career
Hmm.
aspects are fundamentally a little bit competitive, right? I mean, there's a certain number of jobs, there's a certain number of positions. Um,
Right.
and we're lucky that we get to do this, our passion, for as a job, but we have to remember that, it doesn't fully define you. There's more to you than just your job.
Sure. Okay. So the next question is that are there any tips that you can give for people to self-study geometry and topology?
That's a good question. So, uh, my background, I taught myself a ton of geometry and topology from self-study. Uh, for me, it was sort of very disorganized over many years. Um, this was obviously pre-ChatGPT, so I would read Wikipedia, I would read John Baez's This Week Finds. It's a fantastic website. Um,
Did you read NLab?
yeah, from time to time, I find the NLab quite useful.
Sometimes,
I know that's not a
sometimes it's
common.
just
Sorry.
well, it's useful, but it's intimidating. Very, very intimidating.
It's very intimidating. It's written from a from a certain very formal perspective that if it's a formal perspective you can get on board with, it can be very useful. But if it's a perspective that
Mhm.
doesn't, connect to the way you think about things, then I understand why it might be not so
Sure.
useful. Um, Trying to think about other tips for self-study. I mean, I found ChatGPT recently and things like that very useful
Oh, great.
in learning.
Hmm.
I something I needed to learn something about operator algebras recently, and the original papers are very technical and also not written in an expository way at all. And
Hmm.
ChatGPT was able to digest that. That's something I found helpful recently. Um, but yeah, I mean, I would say. For me, it was very disorganized self-study over many years.
Hmm.
So if you have a sort of more immediate goal, I'm not sure I have a very useful piece of advice.
Okay.
Yeah.
Yeah, I agree with you that ChatGPT itself for learning is
Yeah.
very good. I mean, you can ask ask things that you're not sure about, and then, it will generate good answers. Sorry, do you use Alpha Archive?
No, I don't know what that is.
So Alpha Archive is like archive, but like you can comment on papers.
Hmm.
Right. For example, if there is something, I mean, there are a lot more things than that. But one thing is that if there is a paper and then there is some point which is not very explained, someone can ask a question and the author can answer in the comment
Hmm.
section.
Hmm.
That's a very good thing. And so
That
sometimes,
sounds great.
oh
I'll check
yeah,
that. You says Alpha Archive?
archive. I think it was made by it was made by computer science students from
Hmm.
Stanford. So you will see the computer science bias in the whole platform,
Hmm.
because for example, if you want to customize your feed, you won't find high energy physics as a tag. That's
I
bad,
see. I
right?
see. I see. I
But
see.
it's mostly made for people who work on AI and computer science.
It
But
sounds like it'd
this
be great in
feature,
our field.
yeah, I agree.
Yeah.
So this feature is quite good that you can start a discussion,
Uh-huh.
on the side panel of a paper.
Yeah. Yeah.
So that's why I like it. And then there are, the there's an AI that it's inbuilt in that platform, so you can try to find relevant literature for your
Mhm.
problem. So that's why I just love it. There
Yeah,
are
it sounds
some
great.
problem. Yeah, there are some problems in that platform. For example, if you try to connect your Orchid, it's a
Hmm.
nightmare. It
I
just
see.
doesn't do it at all. But yeah, otherwise it's very, very, very good. So one another thing that I wanted to ask you is that on this topic of learning
Mhm.
mathematics on your own. So sometimes what happens is that you start to go very deep into the
Yes.
the pure maths thing, and you just
Yes.
forget that you are doing it for physics, right?
You
uh,
know, yeah. Do you have a specific question about that? I mean, I have lots of
well,
thoughts
I
on
was
that.
just I was just gonna say that I think in 2022 I was learning algebraic geometry,
Uh-huh.
and I just started learning about algebraic geometry about arbitrary rings, and
Yes.
it's
Yes.
a very deep rabbit hole.
Yes.
So yeah, you were saying.
Well, I would say that that was my academic trajectory, 100%.
Hmm.
My interest in this field started from physics, started in fact from pop sci books.
Hmm.
Might be surprising to hear that in particular Lee Smolin's pop sci books were some of the most inspirational and motivational. Um,
Trouble with physics.
Three Roads to Quantum Gravity, more
Okay,
specifically.
that's better.
Um, yeah, well, less critical of string theory at least.
Yes.
I have to say a lot of the principles he emphasizes, holography, background independence,
Hmm.
these are the principles we're talking about. I mean, this
Sure.
Cobordism conjecture is some form of background independence, right? It's some statement that there's no background at all.
Hmm.
Um, but yeah, so my interest started from physics, but I went much further in math much quicker. And I think
Hmm.
some part of that has to do with the fact that in math, the questions, the things you're thinking about are more sharply defined, as opposed to physics. And so I found it easier to
Hmm.
self-study math than physics. One piece of advice I would give for learning, this is actually a piece of advice I got from Natty Seiberg, was that you should learn the physics from the physicists. And I think the converse of that is also true. You should learn the math from the mathematicians. And I think that there's a lot of benefit in, quantum mechanics class, quantum field theory class,
Hmm.
working through the problems, working through the exercises. And conversely, I think it's very beneficial to learn, say, algebraic topology from the mathematicians. You
Hmm.
know, there's a lot. Physicists use things like homology and homotopy groups and things like this very cavalierly. Um,
Yes.
and I think if you really want to feel confident with those subjects, you should learn them from the mathematical perspective, um, and then later apply them to physics. I think that it's difficult. I think it's difficult to learn math in particular if you force it to be always just clinging on to physics. I think that the mathematicians have developed quite a lot that's very useful in its own right. And for me
Hmm.
in particular, it's been very helpful to know math that hasn't been used in a field. For instance, cobordism theory. This is something that
Yeah.
I learned from math, from having
Hmm.
taken math classes, and then finding places in physics where it can be applied.
I mean, so if I think about that, then I would say that the way I learned about differential geometry and fiber bundles, I learned it from a maths perspective.
Yeah.
But take something like, so when people take courses on GR,
Yes.
they learn physics from differential geometry from a physics
Mhm.
perspective. And most people who know about GR, they don't know a lot about,
Yeah.
they don't know that one forms are maps,
Yeah.
right? They just say that, okay, it's a vector with a lower index. That's
Uh-huh.
it. So at least there, it's beneficial for people to learn maths from a physicist. So don't you agree?
I think it's beneficial. I mean, honestly, I think it's beneficial to learn both.
Okay.
I think
Good.
that it's beneficial to have something that has served me very well in my research is just having
Hmm.
a broad perspective.
Hmm.
Um, being aware of things in math and things in physics, the way they're thought about in physics.
Yeah.
Also, more generally, we were talking about how do you, like keeping in touch with like things that are popular ideas. I think it's also been very helpful for me to, you know what's going on in the quantum information community as well as the Swampland program, because I think a lot of
Right.
things I've worked on in Swampland program are motivated by ideas from quantum information. So it can be very helpful to have a broad perspective. Um, so yeah, I'd say for like differential geometry, I think you just learn different things in a GR class than you do in a differential geometry class, and they're both useful.
Hmm.
Um,
And I think when you learn, a particular subject from, a particular community, you also learn the attitudes. So,
yes,
for example, if you learn maths from a mathematician,
yes,
you will probably not make progress on a problem until you have proof of a theorem.
hmm
But like, if you're a physicist, you can just guess the answer. So,
uh-huh.
for example, mathematicians, correct me if I'm wrong, but I don't think that mathematicians think that mirror symmetry is a thing. But physicists do use mirror symmetry all the time.
I mean, I think that mathematicians think a lot about mirror. There are certain mathematicians who think a lot about mirror symmetry,
Hmm.
but I think that to physicists, mirror symmetry is much less conjectural than I think that the mathematicians think of it
Yes,
as.
I should
Yeah,
have said that. Yeah,
yeah,
they
yeah.
have more confidence in it. That's what I wanted to say.
I mean,
So,
from the physics perspective, mirror symmetry. I mean, you just change your notion of your chiral
right.
supersymmetry algebra. I mean, it's like clearly a thing in physics, right?
Yes.
Um,
I remember that in Qumran's book, Puzzles to Unravel the Universe. I
yeah,
think it came
yeah,
in 2020.
yeah.
So in the one of the last chapters of his book, he talks about one problem. If I remember correctly, it was about fitting circles
hmm
in a particular Calabi-Yau space,
Uh-huh,
and
uh-huh,
the problem is that how many of them can you do, given the genus of the Calabi-Yau, which is one, two, and
uh-huh,
then so on.
uh-huh, uh-huh, uh-huh.
And it turns out that using mirror symmetry, you can do it up to genus 46, and mathematicians have only done it up to genus 1.
Uh-huh, uh-huh,
Because they take the results that come from mirror symmetry as conjectures, and they just prove them using their own methods. So you also learn these attitudes. So
Yes.
yeah, you
Oh, I would
do
say
you have
one thing
something?
is this is just part of why I chose to study physics as opposed to math is that you can just kind of go faster.
Yeah.
Um, and of course, part of that means that you're going to break things along the way, and sometimes you'll be wrong.
Hmm.
But yeah, I mean, as physicists, we can sort of skip lightly over
Right,
things
right,
there.
right.
There may really be quite a lot of technical details to be worked out, but you can. sort of go along without having worked them out to a certain
Right.
degree in physics.
I mean,
I would say there's a flip side of that actually,
mhm.
which is something that was something Cameron really had to emphasize to me, and he was absolutely right. And it was a transition from going from math, like math sort of summer research projects when I was an undergrad to a grad student. Is I had this very funny experience where I told Cameron like, oh, I've proved this, some statement, and he'd say, okay, now go check it in an example. And I found I was so confused. I was like, well, I proved it. Why should I check it in an example? I know it's true. And he was absolutely right, is that you should still check it in examples so you really understand it. You really understand how the abstract formalism connects to the concrete thing.
Hmm.
And
Yeah.
sometimes you learn that the thing you thought you proved is not actually the thing that you proved because you look at an example and then there's some subtlety you missed. And so I mean, I think in plenty of mathematics research, this is true as well, but especially in physics research, it's very important to look at examples and
I
to
agree.
connect. Maybe I can say more generally from the question of learning, there's a question of like, is it better to learn from abstract perspective? This is also related to physics versus math, but
Hmm.
abstract perspective versus concrete perspective. Should you learn examples or should you learn abstract theory? And again, I think the answer is really you should learn both. And it's very powerful to be able to go between an abstract theory and an example because then you don't get too abstract because you just know how to apply it to an example. You know what you're talking about, but the abstract theory can be powerful for going beyond examples you know. So I think
Yeah.
it's helpful to have both.
I think even in physics, so
Yes.
I have interviewed two people who were, part of the Weinberg group in the 80s. So
Uh-huh.
one of them is Cliff Burgess, the other one is
Uh-huh.
Fernando Quevedo.
Uh-huh.
So they told me, both of them told me that, there was a difference in attitudes towards doing physics when it comes to, for example, Weinberg versus
Hmm.
Polchinski. So
Hmm.
they
Hmm.
said that Weinberg used to talk about general principles, and
Yes.
if he can make a general statement about physics, and Polchinski used to do that. He said that, okay, can I come up with a model that
Hmm.
captures the things that I want
Yes.
to talk about, and just talk about that model?
Yeah.
So even in physics, this difference between like abstract versus
Absolutely.
concrete happens.
Absolutely. The one part that I just think for me has been very useful is being able to go between the two.
Hmm.
Is
Yeah,
knowing how the abstract idea connects to the concrete example. Um,
yeah.
maybe,
And if you're
maybe,
working on,
maybe, maybe just one comment. We were talking
mhm,
before about how physicists learn differential geometry. We learn a tensor
yeah,
is a thing that transforms like a tensor, and I think mathematicians this drives them crazy. But from a certain level of mathematical sophistication, this is a completely sharp definition of a tensor because that
yeah,
statement defines a sheaf on the site of manifolds. And so it
mhm,
defines a tensor. It tells you a tensor is a thing that you write in local coordinate patches, and as you go from coordinate patch to another one, you transform.
mhm,
And so, for instance, I think you shouldn't be scared of the word sheaf. When you hear the word sheaf, you should think a sheaf is, a bunch of things that transform like that thing. Yeah, a sheaf is just a formalization of the notion of a tensor that is a thing that transforms like a tensor. And so I think
mhm.
that the point of abstraction is not to tell you you didn't know something you already knew. It's to tell you how to take the thing you already knew and then see the same structure somewhere else.
Right, 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 right. I mean, you were saying that what you have done in your research is to go between these two attitudes, right?
Mhm.
I was thinking that if you work on Swampland, you have to do it because you have to make general
Yes.
statements, and then you
Yes.
have to talk about particular examples as well.
Absolutely. Exactly. Yes. We want to make general statements, but the best way to check them is to check them in a bunch of examples and see if they're true.
Right, right. Okay, so I think the last question from the people is that do you have any book recommendations for physics or maths that young people should read in undergrad and grad school?
Do you mean for, say, like technical books or popular science books or
That's what
both?
I think,
Yeah.
technical books, but I think the question is very open-ended. But so I think it
I mean,
means
I
for
would say,
technical
first of all,
books.
for popular science books, I do still think Lee Smolin's book, Three Roads to Quantum Gravity, is
Okay,
still quite relevant and worth reading.
sure.
Um, for technical books, let me think. Um,
Do you like Nakahara?
I've barely opened it.
Oh,
Um,
okay,
I've barely opened it. So I don't really know.
okay. I
Yeah.
mean, did you read your algebraic topology from Hatcher?
Yes, I took algebraic topology from Mike Hopkins at Harvard,
Okay.
largely out of Hatcher. Um, yeah, I think Hatcher for algebraic topology is perfectly good.
What about differential geometry?
Differential geometry. Yeah, this is also why I didn't have a great answer to advice for self-study, because the way I learned a lot of these things is not like from one book. It's from many, it's sort of like a conglomeration of many different
Hmm.
things over some period of time.
Okay.
Sort of osmosis, if you like. But um, I think in terms of maybe one place I can say something that's been useful to me is in terms of quantum field theory textbooks.
Hmm.
The one I learned it from was Schwartz, from Matt Schwartz. Um, and I found it very useful because it really does connect to the actual physics meaning of the things as opposed to dive you in the deep end with, here's the path integral.
Hmm.
Um, I should say actually one thing to I should say is the one topic that I found most difficult to teach myself and really never succeeded in making a ton of progress in teaching myself is quantum field theory. Um, and I think that that was one place where that's actually one place in my own learning of this stuff is where I was trying to learn it from an abstract perspective. I was trying to learn what
Yes.
is a quantum field theory. And what I needed to do was be forced to sit down and calculate Feynman diagrams. And once you do that, I don't calculate Feynman diagrams in my research, right? But almost ever. In fact, maybe never. But that's the sort of advice in terms of it's valuable to struggle through the problem sets and it's
Hmm.
valuable to take it in a course context.
I was gonna say this that that you struggle with quantum field. I mean, quantum field theory is a hard subject to learn,
Yes.
but I think I mean, you said it yourself, but I was gonna say it anyway that you probably struggled because you were trying to understand it from a maths perspective, like from a very abstract,
Yeah, I don't know
rigorous
if like
perspective.
exactly, I was enough of a physicist to want to learn it from a physics perspective, but I was trying to learn
Mhm.
it in the sort of this sort of learn the abstract structure
Right.
way. And what I need to do is calculate, the one loop vacuum polarization in QED. Like, actually, I think that specifically was just so illuminating, seeing exactly how you calculate the one loop vacuum polarization and you see charge screening. Like,
Hmm.
uh,
Hmm.
and
I
then
mean,
that you
but
learn like, I mean, it takes a lot of maturity to understand what quantum field theory is about. It's a very complicated subject, but and that's an example I would say learn it from the physicists. Yeah.
I see. I mean, but this is exactly, not exactly, but a bit like what your advisor went through. I mean, I think
Yes.
Kumran said in the podcast that he was trying to, rigorously write down quantum field theory when he was a
Uh-huh.
student.
Uh-huh.
But
Uh-huh.
then when he became a student of Witten said that, oh, just look at Feynman diagrams as if they are actually if they are actual processes. Although Witten is a very good mathematician, but
Yeah.
he still just took Feynman diagrams literally for physical insight.
I completely agree. Actually, that's there's a whole collection. Occasionally I see stuff like on Twitter. There's a whole collection of things that people say, aren't technically right that I don't know if I agree with. Like people say, for instance, that Feynman diagrams are not actually pictures of the physical process.
Yes,
And
I
I'm
think that's
really not sure
true.
why that's true.
I mean, because so okay, so the thing is that Feynman diagrams, you know, that can only happen if you have canonical quantization. So in path integral formulation, you won't have something like Feynman diagram as particles. I mean, you'll have fields.
Well, but there's a world line formalism of quantum field theory. Of course, it's only perturbative and it doesn't.
Sure.
And yes, I understand the reasons why virtual particles are not quite the same thing as what we mean by, asymptotic
Yeah.
states, but I would also counter with the fact that no one has ever seen an asymptotic state because we don't actually live at asymptotic
Sure.
infinity. Every
I
particle we've ever
mean,
measured is a virtual particle.
yeah. I mean, there are people out there who think that even real particles are not particles. They are just like
Yeah, sure,
excitation
that's
driven
a fine
fields.
perspective. I mean, one thing that Cameron always emphasized, I think, is a good perspective is duality, is that these are two descriptions that are both correct. It's not like one is more correct than the other. Um,
Uh, True. I agree. Actually,
But
yeah.
maybe to just
That's.
give one other example, just for fun, of something that I think is in this vein, is, people
Mhm.
love to say that spin is not like the electron is a little spinning thing. And I just
Yes.
don't buy it. I think the spin is because the electron is a little thing that's spinning, and the spin of it is the fact that it's spinning.
I mean, it's a very good picture. I don't. So I did read an argument for why people say that, but I don't remember it right
Like,
now. But yeah, I mean, it's a very it's a very good tool. I mean, it does give you a very good intuition for what's
Mhm.
happening there. Um, I mean, okay, so what, I don't remember the argument exactly, but I think that the problem was that when you have things which have spin higher than one half, then what's
Mhm.
happening like three half. Then what do you mean by spin like this? And like, why is it quantized? And I think people
Yeah,
talk
I
about
mean,
that kind
of
of
course,
stuff.
what's weird, there's two things that are weird. There's that it's quantized and that that it's a half integer.
Yeah,
Um, I mean, another thing to say is, of course, when you have a big semi-classical object, when you say that it's spinning, you mean you can both have it not be spinning and have it be spinning.
yes,
And when you have a single representation of the rotation group, that's one particular spinning configuration. That's not the object with its, you know, semi-classical object needs both the sitting still and the spinning. Electron doesn't have the sitting
yeah,
still state. Um,
right.
so yeah, there's all sorts of technical caveats to say, but
Oh yeah.
I mean,
I
come on,
mean,
it's a little thing that's spinning around.
true. I mean, these are kind of interpretational. I mean, not always, but sometimes they are just interpretational issues. I mean, for example, another like small article that I was writing with one of my friends for another,
Yeah.
not for a paper, but for like a small magazine, was that does Einsteinian, sorry, does the Einsteinian physics mean that Newtonian physics is wrong? Now, some people think
Uh-huh.
that it is
Uh-huh.
wrong, right?
Sorry?
Some people think that it is wrong, although, and those people are not very familiar with like effective theories.
Yeah.
But from a particle physics perspective, you can see that Newtonian physics is just a limit.
Yeah.
Um, so that's another interpretational issue that some people, have disagreements about.
Yeah, I mean, there's of course semantics and like what does wrong mean, but
Yes.
it's funny. I was having who was I talking? I think it was Clay Cordova,
Hmm.
talking about, you know, do we need to introduce the notion of force? I think it was an interesting question he raised. In most of modern physics, we never talk about forces.
Yeah, we talk about
However, the
potentials.
intuition of what it feels like to push on something
Yeah.
is very useful.
I
So,
mean, when I was in high school, when
uh-huh.
I learned first about weak interaction, I was like, how is this a force?
Yes,
What is pushing on what? But it's like
yeah.
an interaction. Sure.
Yeah. And I mean, yes, if you want, you can describe it in terms of forces, but
Yes.
there's other ways to maybe just sort of a sort of general statement is like it's just useful to have multiple perspectives on things.
Right. But my question was that for the strong force, you can think about that, okay, there's like a force that is, having protons and neutrons in the
Mhm.
nucleus. But weak force changes flavors. What is being pushed? That's something that I never
Right.
understood.
When the most important aspects of weak force are things like, nuclear decay, radioactive
Yeah,
decay, for instance.
right.
Radioactive decay is, I mean, look, you could say that the products of decay were already there, held together by a force, and then one of them came out of the potential well and fell away by a force. You can phrase it that way if you
Sure.
want to.
Right.
You don't have to.
Right. But my question is that, okay, even if that thing is being caused by a force, how can force change the nature of a particle? Like, how can it change the flavor? That's my
I mean,
question.
I totally sympathize with the point you're
Yes.
making. I would just say that I think that there is a way if you want to, which is to say
Okay.
that the particle already was a bound state of the things it decays. For instance,
Oh,
saying
okay.
that
I see.
you know, uh, you know, what do I want to say? A proton is a bound state of a neutron and
Yes.
a positron and a positron antineutrino or whatever. I think I got it
Right.
right. I hope I got it right.
Oh, it's fine. It's fine.
Yeah.
But I think that I can come up with another example. So you're talking about bound state of two
Yeah.
particles. What about neutrino oscillations? There's only one neutrino, but it's changing its flavor as it oscillates, right? So what is
Yeah. I
happening
mean,
here?
yeah, of course, the invariant physics is a question of what are the states, what are the quantum numbers, what are the,
Yes.
you know, um, something I think that is also very much related to the Swampland though is that the idea of duality is very powerful. And I think
Hmm.
that for instance, like take QCD. String theory came out of trying to understand hadron physics, and then we learned maybe it's not the best description of hadron physics, and you
Hmm.
know we have QCD, we have quarks and gluons. But actually, in many contexts, QCD strings are a very good description of the physics for certain properties.
Hmm.
And I think it's not, you shouldn't say that one is right and one is wrong. You should say that they're dual descriptions of the physics, and having dual descriptions is better than having one description, because then you have multiple descriptions and you can use them to
Right.
answer questions that are easy in one or hard in the other. Um,
I see. Okay, so actually, I said that I asked the last question, but this is
huh?
the last question. It says
Sure.
that what major problems in high energy physics theory do you
Mhm.
want to be solved in your lifetime, and you can't say all of them.
And I what?
It says that, and you can't say all of
And I
them.
can't say all of them.
Mm.
Um, yeah, I mean, I think the one that I would most want to see solved is I want a complete definition of string theory or quantum gravity. I want to know.
Mhm.
We had a whole workshop on it at KITP a year or two ago, but what is string theory? You know, we have this
Yeah,
perturbative
saw some
theory.
parts. Mhm.
We think that there's something called non-perturbative string theory, quantum gravity, and I want to see a framework for it. I want to see an in principle definition. There's a question of doing calculations and a question of definition. And I think that for quantum field theories, we have a very good in principle definition. In principle, we know what a quantum field theory is. There's lots of interesting questions about the dynamics of quantum field theory, but I would really like to know in principle, what is quantum gravity? What
Okay,
are the what is the data? If you say that you've handed me quantum gravity theory, what are you supposed to hand me? That's the question I want to see answered. I want to know what does it mean to have a non-perturbative theory of quantum gravity?
okay. Any other problem that you want to be solved in your lifetime?
Um, that is the one I've been fairly single-mindedly focused on.
Okay.
Trying to think if I have a good answer to that, or the answer is really no, that's the one I care about.
Okay, it's fine. You don't have to say.
I think that's the one I care about
Sure, no problem.
overwhelmingly more than any other. Yeah.
Okay.
Yeah.
So I think my questions are over. Thank you so much
Yeah.
for your time. It was a
Yeah,
long
absolutely. This was a
podcast,
lot of
but
fun.
thank you. So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.